make climate software better. And that might be adding new features, making it faster. One of our main efforts at the moment is helping researchers add machine learning into their existing climate models. If you want to find out more, there's a QR code and you can visit the website. As far as I'm aware, all of these slides are being made available and they're on the Google Drive, so please feel free to download and you can click the link if that suits you. So tomorrow, my colleague Chris Edsall will be giving a talk explaining exactly what the ICCS is in more detail. Annoyingly, we are kind of out of order, but if you see his talk tomorrow, then you'll be like, yes, now I know what ICCS is. So please go along to that. So yeah, I'd say we are in a climate crisis, unfortunately. There are rising global temperatures, there's increased food and water scarcity, and we are seeing new extremes, kind of new records broken every day, and they're not good records, both in terms of the magnitude of these events and also the frequency of which they're happening. And there's like sort of knock-on effects, multiple events get chained together, droughts followed by floods, etc. So yeah, so things are not looking good. If we want to mitigate climate change, we first need to be able to measure it. So it doesn't matter what policies we come up with, what ideas we have. If we can't measure what's currently going on in the climate and also what effects our policies or changes are having, then we're not going to be able to say if one policy is good or bad, right? So it's very important that we are able to measure our kind of the impact on the climate. So how do we do that? Well, climate modeling is the way to do it, is one of the ways to achieve this. And kind of by and large, climate model accuracy or improvements to that have largely consisted of turning 3 dials. So we can add new physics, we can increase the resolution, so run on a finer grid, or we can try and use better parameterizations, okay, for the things that we can't resolve. No problem then. We just need a bigger grid, finer grid, possibly a bigger computer, and then we can run more accurate models. Well, unfortunately, the pursuit of accurate climate modeling increases computational complexity, things like, communication bottlenecks and putting stuff into memory and maybe putting stuff onto GPU. But this increases the time to science. Okay, so time it takes scientists to have an idea, implement it, run the calculations, and get the answer. And it's also increasing the energy consumption. So climate modeling is a main use of high-performance computing, and high-performance computing is a main use of energy. So we want to be able to try and reduce that where possible, but more and more demanding models will require more and more energy. Can't AI solve this? Probably thinking that. Some people might be thinking that. Short answer is yes, maybe. So certain types of problems can be solved by AI, and it can lend itself naturally to certain types of problems. But there's a barrier, right? So AI machine learning is typically implemented in Python. There's libraries such as PyTorch, TensorFlow. But climate codes and climate software, on the other hand, is typically written in Fortran or maybe C++. There's a Julia model that I know of, but yeah, and Fortran models, we've got some examples, so CSM and also the Met Office have their model written in Fortran. So trying to interface between Python machine learning side and chucking that into climate models can be a challenge. So what are some possible solutions that you could take? You could implement a neural net yourself in Fortran. There's a package called 4Pi you could use, there's SmartSim, and there's Fortran Keras Bridge, and there's some other options as well. But I guess some reasons why you wouldn't do these approaches that exist is, so implementing a neural net in Fortran, well, if you do it yourself, it's error prone. You should always try and use existing libraries where possible. If your neural nets change or increase in complexity, it may be difficult to add that functionality. You're going to be kind of constantly playing catch up, because as new things get added to say Python and PyTorch and other packages, then you're going to be playing catch up, and that takes a lot of development effort. And you need to be able to verify that these things are correct, where there's a lot of current developer effort and testing and communities behind the Python implementations. 4Pi, to my knowledge, I'm not involved in that project, but it looks like it hasn't been maintained for a little while. So I've taken that as the last commit was 3 to 4 years ago. And another consideration is it uses the GNU public license, GPL, which I know for certain some governments or organizations and projects aren't willing to work with the GPL license. It may or may not affect you, but it's worth being aware of that. SmartSim, this is like a kind of client-server type model where they kind of, your job runs and it submits kind of saying like, hey, can go and run this on GPU and then come back and give me the answer. It's a little bit more complicated in terms of setup and configuration. And again, to my knowledge, from documentation, it looks like it runs on NVIDIA only. So if you have AMD GPUs or Intel GPUs, it may or may not work for that. And then the Fortran Keras bridge also looked like it wasn't maintained. I think last commit was 3 years ago for that package. So this brings me on to introducing our approach, which is FTorch. So we try and take advantage of PyTorch's C++ backend and API. We use the fact of binding Fortran to C is kind of straightforward, thanks to ISO-C binding. That was brought in Fortran 2008, I believe, and improved subsequently. We can also we also take advantage of the fact that PyTorch provides this thing called Torch script, which is like a high performance runtime, and you can take a PyTorch model and sort of like, I say export because it's not quite compilation, but you can basically trace or script your PyTorch model and convert it to Torch script, which can then be run on a GPU. And the other key thing that I think is important is we provide what I call a Fortran only interface, which means if you're a Fortran developer, you don't need to know the C++ or C or understand how C binding works to use our library. You can just code in Fortran, and we've tried to make it like a Fortran friendly interface that can accept, like, Fortran objects, things like that, Fortran arrays. So that's kind of one key advantage of the FTorch. If you're familiar with Fortran already, there's hopefully less learning to do. There's a link to the GitHub repo, and this will be clickable if you download the presentation. So some of the benefits of this library are that we don't do any memory copies. So there's some pointers handled in the background. Again, the user isn't responsible to do that, but it just means that you're not having to copy memory. Whereas I think in the SmartSim approach I mentioned earlier, there is some kind of copying of data that goes on. So it's worth being aware of that. Simple, which is fair for me to say, but we have a CMake installation build process, so hopefully it is simple for people to add that into their existing builds. We have relatively few dependencies, so you need libtorch or PyTorch, but you possibly need that anyway if you're generating your model in Python or using PyTorch. So yes, that's a dependency. It can run on GPU or CPU, so there's just like a variable you can switch in the code in the Fortran API, and you can tell it, hey, I want to run on CPU, I want to run GPU, and there's no vendor lock, so it should run on different, not just on NVIDIA GPUs, if that's important to you. It can run on multiple GPUs, and by that I mean simultaneously. So it can run on, like, if you've got a node with 4 GPUs, then it can use 4 GPUs. It's multi-GPU aware. Okay, so they each have like an ID. Fortran only, so I mentioned this already. We've tried to write it to be as friendly to Fortran users as possible. And there's less boilerplate code when I compare to the alternatives of 4Pi or SmartSim. So for like an equivalent type calculation, there's less additional code you need to write. And we also provide, it's licensed under the MIT license, which is one of the most, I guess, flexible licenses, like BSD, etc. So if that's important to you, then yeah, that'll be a factor to consider. Also, so 4Pi, which I mentioned earlier, relies on having an active Python runtime environment. And on HPC, this can be a bit of a challenge. And it can be quite tricky to link to this Python environment. So we've got a nice XKCDC. I always have too many letters, but we've got a nice comic there. So I want to kind of demonstrate what kind of changes would you need to make to your code in order to use FTorch, the library. Well, we're going to have a look at the Python side. So we'd assume that you have some kind of model that you've pre-trained in Python. In this example, we're looking at ImageNet, which is an existing ResNet model. So you need to import your Torch Vision stuff as normal. You kind of load your pre-trained model and you pop it into evaluation mode. I've got a dummy input here, which was needed to kind of trace this model. And then we effectively, I'll say like compile in inverted commas this to TorchScript. So we output it or export it to TorchScript in a process that's called tracing. So we have the line .trace, and we pass it the dummy input so that it basically runs like a dummy run of your neural net. And then it says, oh, these are the operations I'm taking, and it exports that to TorchScript. Okay, and then that can be used externally. So then the next stage is, what do you do on the Fortran side? Well, once you've traced your model, you go to your Fortran code, you're going to use FTorch to import the FTorch library. Great. We're going to define a model. Okay. This next bit, you'd have bits of this in your code anyway, but this is just some kind of declaration of variables that you'll need. So we need input data and output tensor. Oh, I think I've got a typo. There should be input and output data and input and output tensors. But you effectively initialize this stuff, and then we'll use it a bit later. We're going to load our model. So this is the thing that we've already saved. So that in the previous step, we saved this as a .pt file, and then we load it in. This is like some pseudocode, but we could say like, in reality, you'd have your input data already. So if you're swapping out a parameterization in your code, you might have some, I don't know, wind velocities or something that you're going to put into that. And so these would be your input data. You create these tensor objects. So these are the things that go in and out of the model in the inference stage. And then the next bit is we call module forward. So this is actually running the inference. Okay, so it takes the model that we've loaded, it takes the input tensor and the output tensor and the number of inputs, and then it actually runs the inference stage. We then have a little bit of cleanup because we want to get rid of these objects if we no longer need them. And then the key thing is, because we've used pointers under the hood, you don't need to like post-convert this output tensor back into your output data. It's already populated in the out data because of the step we took earlier. So now you've run your inference, you've got your output data, and now you would use it in your code as you would normally, in any other bits of the subsequent functions that need it. So that's kind of the steps. And then again, there's a summary. So I'm hopefully demonstrating that there's not too much that you wouldn't already have. So it's basically, importing the module, loading your trained model, and then we run the inference and then do some tidy up. Okay, but again, this is all available online, so you can have a look. We also have some examples in the FTorch library that you can look through and see kind of how we've got like a ResNet example, a SimpleNet example that you can take a look at. So let's go on to some results. We've got a case study of MIMA here, which was a gravity wave parameterization in MIMA. It was based on an atmospheric model, Yucca and Gerber. And basically they replaced the physics-based gravity wave parameterization with a neural net. There's some details of the neural net below, but it was emulating Alexander Dunkerton, gravity wave parameterization. It's a fully connected multi-layer net, and the original work that this is based on was done by Espinosa et al. And there's a link. You can see the paper there if you download this presentation. So we're going to have a look at some results. So on the left, I've got this MIMA case study that I'm mentioning, and on the right, we've got like a sort of a benchmark that just runs like a ResNet example, like a simple ResNet check. And what we do is we run it 10,000 times, and we're just checking the inference stage. So we've got all the input data sort of pre-ready, and then we're just running the inference stage 10,000 times and comparing the timings between a similar approach using 4pi. Lower is better, and so FTorch is consistently faster, but it's not by a lot. I mean, the point of this isn't that, oh, FTorch is 2% faster or 10% faster, so switch it out now. The key thing that we wanted to iterate is that it's just as performant as 4pi, but we have a lot less boilerplate code, and we think we've designed it to be as easy as possible for other Fortran users to take that on board. Similarly, we've got some examples running on GPU. So the previous example was CPU only, and we used sort of a different number of OpenMP threads. And likewise, running on GPU, we can see similar results again. That the FTorch is faster, but it's not. It's not. That's not the purpose of this. The purpose is to make something that's easy for developers to take and use in their existing Fortran software climate models. So yeah, our design goal around this library, to reiterate, was computational efficiency. So it's just as fast, just as performant. There's no additional memory copies, but it's also, we're targeting developer efficiency. How easy is this to maintain? How easy is this to code in the first place? And that brings me to some conclusions. Machine learning has the potential to vastly improve climate models, but leveraging it effectively requires a lot of care. We think FTorch allows easy and efficient deployment of machine learning within Fortran models. Minimal changes are required to extend existing codes. It's designed to be simple and familiar, especially for Fortran developers. FTorch has less overhead than other methods, I mean, in terms of boilerplate lines of code. It's also, in terms of computational efficiency, because we don't do lots of data copies, and there's not a load of extra objects generated. And currently there's an ICCS fork of CIME, SIME, I think it is, implementing FTorch within CSM. So if you download this or want to go to this this link, then you can see how an example of how FTorch is being used there. It's pronounced seam. Yeah, there we go. I knew it. Anyway, I'd like to say thank you for listening, and thanks to my collaborators. So I've highlighted two especially. So Jack Atkinson's been sort of leading a lot of the development on this recently. He also has given many talks on this, and so if you can see slides and some video recordings here. My talk today is based on his slides, and also we had a placement, industrial placement, Elliot, that was working a lot on these codes and did a lot for the GPU stuff. So yeah, thanks to them as well. If you have any questions and you'd like to get in touch, please email me. This is my personal, my work email, but contact me there directly if you have any questions. I'd like to say thanks to Schmidt Sciences for funding this research. And also there's a link to FTorch and a QR code if you would like to scan it. Thanks very much.
Yeah, thank you, Tom. Great work. Do we have any questions in the room or on Slido? We have a question in the room coming.
Hi, I'm Jim Edwards. I'm a CSM developer. I think I helped with the FTorch port there. So 4Pi has an advantage in that you can call interface with all of Python. You're not limited to the Torch library.
Yeah.
Have you thought about the possibility of somehow combining 4Pi and FTorch? So you get the advantages of FTorch, but you also have access to the rest of Python?
Yeah, I mean, so there's nothing to stop you using 4Pi as well. So even if you use FTorch for your neural net inference stage, there's absolutely nothing that stops you from using 4Pi as well. What I would say is, maybe if you were thinking of some deeper kind of cross use of both of them, that actually what we've done with 4Pi, and the reason we've done it this way, is we've eliminated the need for the Python environment at runtime. So actually FTorch doesn't use Python at all at the time of running, because it's taken that pre-compiled Torch script version of the code. And so you're running through a C++ backend, like a C++ API. So again, yeah, yes, you could still use 4Pi and do some Python stuff on the side, but you wouldn't be able to like more closely interact with the model or something like that, because it's already been pre-compiled in a sense to this Torch script variant. Thank you.
Do we have any other questions for Tom? Not seeing anything on Slido. Okay, we have another question coming from the room.
So exactly what will you use it for in SEAM?
Yeah, so I'm not on that project, but the idea is to replace specific parameterizations. I think it might be, so again, I definitely check with, so Jack Atkinson's working on this project, and the idea I think was to replace some of the circulation, the convection, but I've not actually been involved in that project. So I think it's a circular convection parameterization that they're trying to replace.
There was a thank you for that. Any other questions from the room? Okay, let's thank Tom one more time.
Great, thanks very much.
Okay, next up we have Brian and Maull for modules to containers, reducing barriers to crafting HPC containers.
All right. Good morning, everybody. Yeah, so this talk, we're going to co-present it, me and Trahan. The title of the talk is Modules to Containers, and that's fundamentally the idea of it. So we have, our HPC user environment on our clusters, primary cluster derecho, and then the analysis cluster called Casper here at NCAR. And we've gotten some feedback from some users that they would like to, they appreciate the way that we've set up at least some parts of our environment. And they'd like to take that and sort of replicate it at a container environment that they could run maybe on a testing platform or for like tutorial purposes or things like that. So really, leverage some of the work that we've put in crafting our environment, especially for our, the common CFD models that run at NCAR. But, certainly without a lot of inside knowledge, it can be hard to replicate what we're doing. We've tried to make that more transparent, but we want to go beyond that and even try to, really make it, I don't want to say like a one-click process, but as simple as possible to take, your module environment on one of our systems and turn it into a container. So that's the idea of this project. See if I... yeah, so, I probably don't need to sell people in this room on containers, but I will anyway. So, a lot of the promise of containers in HPC, if you're a user of HPC software, you have to deal with complex build and orchestration systems. A lot of this is simplified via package managers, obviously, and that's going to be a fair chunk of the talk, talking about SPAC, which you heard about on Monday and maybe you use. But often you still have to deal with these complex build systems, and the less of those that you have to be intimately familiar with and deal with, probably the better for your life if you're trying to get science work done. There's also a lot of, I would say bespoke design. So like, it's very customized for a particular system or a particular environment, and it can be hard to port those from one cluster to another. I can think of, some build systems where, you just have to you basically input an entirely set up customized, build infrastructure. And if it's not available for your system, then, that's annoying. So if we can pretend it's a different system entirely in a container, then maybe that simplifies that a little bit. And there are, plenty of projects where it's really a core fundamental library or some piece of infrastructure, but the maintenance team for that package has dwindled, or maybe it's even disappeared. So it built great and it ran great on a software stack from 10 years ago, but circa 2024, it's problematic. So again, one solution there is to just find somebody to inherit the project and make it work better on modern computers. But in the absence of that, obviously there's practical problems there. Again, maybe we can recreate the old environment from 10 years ago in a container, and it might just work okay. So this is, just some aspects that make software containers appealing. in an HPC context. They can standardize the build steps, they can reduce specificity, and they can insulate your workflow from changes to the environment. So that all sounds great. And I have just a litany of various HPC container runtime packages here. So, Apptainer / Singularity, got Podman, Charlie Cloud is the only one that doesn't have the name on the right. So kudos to them for being unique. And then, Docker's sort of the fundamental container building technology that everybody knows and loves. But that's all good. But there's certainly challenges with HPC containers as well. And we like to emphasize in our consulting group that they are not the solution to all problems. And they also introduce some problems of their own. A particular one in an HPC context is where are end users going to build their containers? So there are some solutions here now, but in general, people like to use Docker. It's the most used tool for building images, but it has some permissions requirements, escalated permissions that make it unsuitable for use in a lot of cases in HPC environments. So oftentimes, even if you want to run a container in a particular HPC system, you have to build it somewhere else off-prem. And that can be a little annoying. And it can also be a little internet heavy. So another issue is that HPC systems have proprietary software libraries that are impossible oftentimes, or maybe it's possible, but it doesn't really make a lot of sense to install within a container. For example, on our system, we have a lot of HPE Cray software stack. And while that is, they are starting to offer that in container distributions, I would say the implementation there is still, it's pretty early days. And some of the stuff just doesn't really make a lot of sense to be in the container anyway. We do have some developments there that have really helped though, like ABI compatibility with open source alternatives, especially in the MPI space, has been a real boon. So, on the MPitch side, for example, like our MPI library on-prem is Cray MPitch from the Cray software stack, but that should be runtime compatible with other MPitch variants. And we see that with a little bit of effort, that is the case. So that can help run containers even if we don't have the system MPI in the container itself. One other issue, it can require pretty extensive investigation and trial and error to learn how the HPC software stack was built and to reproduce it. And I would say this is particularly a problem given the fact that containers can be very attractive to people who don't want to be Linux system administrators, but you sort of, if you're going to design a container from scratch, you're going to design your Docker file from scratch, oftentimes you have to have a pretty solid understanding of like operating system libraries and packages, and you need to have a good understanding of running the OS package manager like apt-get or yum or zipper or something like that. And that's stuff that like typically on an HPC system, the system administrators would handle for you. But now that you're trying to run a container, or well, run a container is one thing, but if you're trying to build a container, you may need to, know more about that than you may want. Especially if your typical environment's like a Windows machine or something like that, you may not use this on a regular basis at all. So, these are all challenges, and some of which are, they're all handled in different ways. The last challenge of trying to figure out how to build the container is really the focus of this effort and what we're trying to facilitate and to make easier for our users. So with that, I think I will hand over to Mia. We're going to hand off a couple of times to keep things fresh.
Yeah, I think it's like 3 slides. So yeah, get ready for a lot of variation here. Anyhow, here's our big goal for this project. Make it easy to recreate an NCAR HPC environment in an image, right? So this kind of boils down to like one big question, like what's in an HPC environment, right? Well, obviously there's an operating system, right? Like that's one key thing in there. There's a bunch of base libraries and headers. There's a bunch of loaded environment modules too, right? So if you wanted to have this customized, you would use lmod to go ahead and load those things. There's some shell customizations. And lastly, there's some virtual environments. Now, we don't need all of this for our container. We generally need only about 3 of these things. So we need an operating system, of course. We need base libraries and headers. We also need a loaded environment, and we need all the loaded environment modules to go ahead and dynamically be added to the container and built in one big, nice process. So this is our kind of like NCAR ev containerize goal here, right? We're going to select a representative base image and then add a bunch of default software packages that are available on our HPC. Then we're going to go ahead and pull all the software that's built in your modules, right? Or you load it up in your modules. And then once that all goes down, then we'll go ahead and produce you a Docker file to go ahead and build. Okay. Cool. So this goes down to another question about how our software is actually managed, right? So this is how we do it. This is NCAR started using Spec to manage HPC software in 2023, if you haven't noticed. Yeah, it's been pretty interesting so far. But yeah, generally how this all works is that we have a fork of Spec, right, called NCAR Spec, right? This has a bunch of little changes that we went ahead and modified with Spec to go ahead and like make our experience actually managing this thing a little bit easier. This goes ahead and ties to a bunch of Spec environments here, right? We have two in particular, our build environment and our public environment. That's the one you all use, or if you do use our system, that's the one that we currently use. And this forks over into two different paths here, right? A view, right, with a bunch of base packages in it. I'll go into that in just a second. And the Lua modules that we go ahead and, make available for people to go ahead and load. Okay. And lastly, all this is then forked over into, or not forked over, it's represented in our spec-host GitHub repository, right? Almost like public documentation to show you what packages are in there as well as build recipes. Okay, cool. Now just to touch over what a view is essentially a collection of different packages. So when Spec installs a bunch of things, right, it goes ahead and puts them in a bunch of like inconvenient locations, right? Like it's not super familiar to a lot of people. So what a view is essentially a collection of those images or of those packages. And we go ahead and clump them up in what is effectively a /user inside a Spec directory. Okay. So yeah. Now, so once we have all these now that we've discussed these two things, we're really trying to assemble all these puzzle components to go ahead and build these images, right? So we have a few key points here as well. Since images are built off-prem, we need to provide a bunch of users with a bunch of specific features here. So first, we need to provide them the recipes, right? And how the packages are built in our environment, right? We can go ahead and kind of check this off already because we already do this with our Spec YAML configuration on like our Spec, Casper, and Spec Derecho directories, right? Next, we have steps for installing the packages in the image. So we need to actually have those as well, right? But yeah, but it's currently not, well, we have it now, of course, but yeah, that was something that we're still working on. Next, we have binary builds of our Spec-based HPC software, right? This is something that we also worked on in this project. Basically, we don't want you to download all of the tarballs, right? And do all the installation process yourself because that takes forever, okay? And lastly, we need to have a base image that looks a lot like our clusters, right? So we have a bunch of specific little minor features, right, that go ahead and customize to go ahead and, yeah, essentially, and we need to make it look just like the HPC. So yeah, thankfully, we already had 1 and 4 at the beginning of this project. Of course, our Spec GitHub and our potential base images provided from a colleague, Ben Kirk. And yeah, lastly, we need some documentation to go ahead and wrap that all up. And that's something we haven't finished yet, but something we're gonna be working on. Okay. And lastly, we just want to touch on 2 kind of like final little points here, right? So to go forward with this, we really analyzed 2 major components to Spec because Spec actually offers some nice containerization options already, right? But they weren't completely sufficient to what we needed entirely. So we went ahead and started investigating these to try to like extrapolate them a little bit further. The first one's the Spec build cache push. We didn't really go this way. We looked at it and said, this is a little bit too hands-off, right? We need a little bit more control. And lastly, we have Spec containerize, which is pretty simple in terms of how it's actually constructed. It literally just generates a Docker file, right, using your Spec environment. And yeah, this is kind of our target in terms of how we actually built this thing.
And thanks, Mia. So yeah, that's sort of the fundamental design that we're going for here. I guess this part of the talk really goes into modifications that we had to make to what we were already doing with SPAC to support this project. Because a lot of what we had in place worked well for the HPC software stack maintenance, but some of those design decisions then in retrospect, if you wanted to actually use what we're doing on a different system, may not be ideal. So the easiest thing to resolve was the binary build cache. So we were already doing this with our software stack. Basically, we have, I'll show you on the left side here. So in the before, we actually have two SPAC environments. So an environment is SPAC is somewhat similar to an environment in like Conda. Obviously, there are differences, and it's not as isolated, I guess, as a Conda environment. But the idea is similar, that you could have one clone of SPAC and then have multiple different SPAC environments that have different packages in them. So it's sort of a nice way to have the same general infrastructure, but have multiple sort of deployments of SPAC. And we leverage that to have this multi-step process for deploying our software stack. So we have a build environment, which allows us to do a lot of testing of packages. And also we can work with users to validate like an install. If somebody requests a new package and we build it, but we don't really have a lot of experience with it, we can create a testing module, point the user to it and say, hey, check this out, make sure it looks good before we show it to everybody else. But then we don't want to rebuild everything in a public environment that's visible to everybody. So we have this, we have a binary build cache in the middle. So what SPAC can do is it can take a source build and then turn that package into sort of a, a binary distributable, ball of stuff. And then you can reinstall it into any other environment as long as it concretizes the same way. And I appreciate your talk on Monday, Alex, because I don't have to go too much into a lot of this stuff since we're all at least familiar. But the problem with that was our binary build cache was hosted on our parallel file system, which makes sense for our HPC software stack, but it's not visible outside of the HPC. So what we did is we basically re-engineered this to put it onto our object store, which is called Stratus. And this is roughly publicly accessible. You need to be behind our VPN. So we may end up finding a different home for this when we're outside of like a testing phase. But right now that's, that works for our purposes. And it's the same basic workflow now, but instead of going from the build environment to the disk, we go from the build environment to the public object store. And then we install back into our public tree. And again, this should have HTTPS access, which is great for running Docker on a different system, again, as long as you're within the VPN. This slide starts the, I'm going to complain a little bit about SPAC part of my talk. And I should say, I think SPAC has been great, and I would recommend it to anybody who needs to manage software deployments in an HPC style context, maybe even outside. But there are some challenges for sure. So the SPAC concretizer is what decides how a package gets built in terms of like the dependencies and which options are used and all of that. And if you're trying to replicate 2 installs, it can be pretty fickle, especially depending on how you've configured it to behave. So I would say, a big challenge, perhaps the challenge of this project, is getting the SPAC concretizer to behave consistently. We had a number of problems with this, and we found a number of solutions. So problem 1 was the default behavior since a few years ago in SPAC is to have this notion of reusing packages. And basically what that will do is, if there's a package that roughly fulfills the requirements of a dependency, it'll try to use that rather than building building what it thinks it should build in a vacuum, like if you didn't have any packages already installed. This is nice in a lot of contexts because it reduces the number of rebuilds that you need to do. Like if I have, let's say, a version of CMake that would work, but it's not the latest version, then reuse will tell it use that version that'll work. Whereas if you have reuse disabled, then it'll build the CMake that it would, assuming it couldn't find anything on the system. The problem with reuse is that it makes the install order matter. So if you have an existing thing already there that it can use, it will use it. But if it doesn't, it's going to build perhaps something different. And we saw that, like this example shows this. These are just 4 packages that I randomly picked that have some dependencies to them. Don't worry too much about the details here, but the point is, on the right side of these boxes, there are some hashes which indicate basically it's the unique identifier of how a package was concretized by SPAC. So if it's a different hash, it's effectively a different package. It's a different rendition of that package. So you can see here that depending on the order of how I've installed these, I get different versions of TCSH and less. And that's not great for reproducibility, because if I want to build a container that only has some of this stuff, then I may end up with different versions of these if the user actually doesn't, sub-select all 4 of these packages in that order. Fortunately, there's a relatively simple solution to this, but it does mean that our existing deployments aren't appropriate for this project, our existing software stack deployments, because we were using reuse. So in the future, we're going to turn this feature off, and that's going to make things a lot more consistent. It'll be a little bit more work up front in terms of like making it so our HPC software stack isn't super bloated, but I think that's pretty approachable and doable. Problem 2, and this one was a little bit more devious, I would say, is that the SPAC concretizer will try extremely hard to ignore anything that would need to use a deprecated version of a package. So in SPAC, you can mark a version of a package as deprecated, and that sort of tells SPAC, like, don't use this. And you can force it to use it in various ways, but that has consequences down in the dependency tree. So the big problem for us in this case is actually with OpenSSL. So OpenSSL has lots and lots of versions, and generally only the newest ones are sort of permitted to be built by SPAC. All the other older ones are marked as deprecated, and there's good reasons for that. I mean, there are security implications and all of that. However, the operating system that you're using comes with a version of OpenSSL, and that's sort of been built, and it comes from a trusted environment. And they actually tell you in the SPAC documentation, you should probably use that, because if you build it in user space, it's not going to be a trusted build of OpenSSL. So if you follow that guidance, then you end up using this version from the operating system that's probably old and deprecated. And then SPAC really tries hard to not use that as much as possible. Like for example, if there's a feature in your package that then requires a curl dependence, it'll turn that feature off without really telling you, unless you require it to use that feature, because it wants to avoid this deprecated version of OpenSSL. To me, these are at odds and frustrating, and I'd like to see some improvement there. I can think of various things. I just haven't, and maybe there is like a good, robust discussion going on in this in GitHub. I'm not sure, but what our solution was for expediency was to just edit the OpenSSL package in our fork to undeprecate our operating system version to avoid that problem. And we'll see what we end up doing, in the long term. Finally, this was kind of an interesting problem. So if you just clone SPAC and you never make any changes to it and you deploy a software stack, then that's pretty simple. But we have users, and I think we also as a consulting team don't really want to deploy entirely new versions of the software stack too frequently, but there are new versions of packages that come out that people want. So what we do is we'll like cherry pick versions of newer versions of packages, or we'll actually make edits to packages sometimes ourselves to bring new versions in. Like if a new version of NetCDF, for example, came out, we'd want to deploy that into our existing software stack versus saying this is a trigger for creating a whole new deployment. The problem with that then is that there's drift in the sort of the coherency of the entire repository of packages that comes with SPAC. So if like something uses NetCDF as a dependency, then it may have concretized differently in that older state of SPAC than it does in the newer state. And this obviously makes replication hard, because then if you clone the new version of SPAC, like the new, with all the changes that you've cherry picked in, it's not going to build the same way it did when we installed NetCDF back, a year ago or however long it was. So we thought of a bunch of different ways we could get around this. And what we ended up deciding to do was And again, we're going to do this moving forward. We haven't been doing it in the past. That's another reason why our existing deployments don't really work for this project. But we're going to require it that whenever a package gets published to the public version of our stack, it has to, like any changes to the spec repository itself, the Git repository, have to be committed. So we can track that Git commit hash. And when we create the Docker file, we can sort of move back from backward to forward in the history of the state of spec to ensure that that was the same. Hopefully that made some sense. I know there's a lot of term overloading here in terms of repositories and hashes and stuff. But basically, we're trying to track the state of the SPAC repository through time so we can replicate it regardless of how it's changed. And that's actually a feature I'd like to see in SPAC itself. So maybe we'll look at trying to, upstream something. But we need to have some conversations there first to see if it's sort of worth the effort and of general interest.
Okay, taking over again. Okay, so now that we've identified all the different problems here, right, and all the things that we ended up needing to like work around here, we needed to go ahead and start building our builder image here, our base kind of like starting point. So SPAC containerize the actual application inside SPAC, right? That allows you to go ahead and containerize things. It requires kind of a base image to go ahead and start the construction process, right? This is pretty nice for SPAC because SPAC actually offers a variety of builder images to go ahead and construct a container environment for you, right? With SPAC already installed and with SPAC able to install a bunch of things right inside that container. Right. Unfortunately, these builder images lack a lot of the customization that we needed that existed on Caspar and Derecho. So we had another goal, create our own builder image with all the changes that we needed, right? And then essentially have that kind of produce, or we use that to go ahead and produce the Docker files. Okay. So we went ahead and moved on with builder image construction. So we first started using Ben Kirk's container. So Ben Kirk's base image, right? That already had a bunch of the customizations that we needed within Derecho, right? And we went ahead and added all the stuff that had SPAC all had, right, inside its builder images. Right, had that all kind of conglomerized into one nice little package, right? And then we went ahead and made sure that we were using NCAR's fork of SPAC and made sure that was inside of our image, okay? Once that all happened, then we needed to go ahead and start adding our SPAC view to it too, so we had more of a fundamental kind of base, right? And this is actually gonna be an option that exists inside NCAR Containerize, but yeah, once the builder image is constructed, then we go ahead and start using SPAC to install a bunch of useful packages that users kind of need for their general workflow if you plan on using this image, like, more generally. So we went ahead and started looking for a subset of packages, right, that exists inside the view as I described earlier, right? And we went ahead and tried to customize this. I guess we didn't use the builder image for that, but we went and used the builder image to go ahead and construct another image, right, that had all those nice little features in them, right? So these view packages basically are very low level kind of subset-y, like, nice utilities, right? Like, stuff like CMake, Vim, GNUplot, Qt, right? Things like that, right? Some stuff that's like super fundamental for a lot of packages. Okay. Once we had all that kind of information, we compiled that list. We went ahead and utilized spec containerize to go ahead and create a Docker file. We made some modifications to that Docker file and made it a little bit more custom, right? Including stuff like including our own custom repos and things like that for choosing and building our own kind of like recipes and whatnot. And lastly, we applied a little bit of post-processing. Lastly, we went ahead and tagged it and built the image, right? And then we had that available to go ahead and iterate on, right? And build more packages on to have a nice kind of like concise flow, right? Using our base view. Okay. So now that we have SPAC mostly behaving and we have our builder image or our view image at this point, we can go ahead and layer on customizations that people like are specifying using their module load commands, right? So this is our NCAR containerized application. This is the flow of how it works. So first thing it does is set up the correct SPAC in the shell. right? So it goes ahead and like modifies things and makes sure spec is all good to go and loaded. Then it goes ahead and creates a temporary spec environment for you, right? This is required by spec containerized. So you need to have a temporary kind of spec environment to go ahead and use that feature of spec. It goes ahead and filters some unnecessary YAML settings, right, that exist inside our spec kind of settings, right? So it doesn't need to have those. It goes ahead and removes any HPC file paths and externals as well. So it goes ahead and chops off a few of those little smaller nitpicks, right? Things like, you know, a build directory that exists on Scratch Derecho or something, right? Like, you know, things like that. Then it adds a container YAML config, right? And lastly, it'll go ahead and run spec containerized to go ahead and get all that information to a nice Docker file, right? And lastly, yeah, we do a little bit of module customization to set everything all up. But this is our usage options here, right? So, you know, basic kind of view here, right? But yeah, that's essentially our application here.
Yeah, so to sort of summarize the changes that we do, you know, really a lot of this is like spec containerized functionality. The changes and spec containerized generates the Docker file based on the environment that we construct, which again is informed by the environment modules that you have loaded when you run this utility. The changes that we make to the resulting Docker file that spec creates and sort of the value add, hopefully, that we're giving is first off, we're adding a public GPG key that's trusted from our binary build cache so that it'll use that instead of trying to rebuild them. This is a step that, to my understanding, it won't do itself, but we sort of just insert that. And then the bigger change, again, goes back to tracking the state of our spec repository. So the old logic, it just, you know, this is like a Docker run command. It will activate the environment and install all of the packages at once and then do some garbage collection. Whereas what we're doing is we are sort of installing them sequentially, which doesn't really add much time because we're using the binary build cache. But when there's a change in state that we've detected from this registry of what the spec clone looked like, at the time the package was installed, we can then do sort of a sparse checkout of that version of spec before we install the package. So we make sure it looks exactly the same as it did when it was installed into the HPC software stack. And that will, you know, there'll be a loop of however many packages it needs to install based on, you know, however many modules the user has. Here's a simple example, and it's simple because we still have a lot of work to do. But so if you ran this utility, basically it's, you know, it's going to go through, it's going to create that Docker file, and then it's going to look at the modules that you have loaded. So I have some very simple ones here. I have tree, Z standard, and flex, as well as conda. And basically it infers what was installed. It's going to skip certain ones currently because those are excluded for reasons like we don't support conda because, as we've talked about, I think this week, conda and spec are somewhat orthogonal approaches. But the other three get detected and then they get installed by this utility. Well, I guess they get installed by Docker, but they get put into the Docker file by the utility. And then if I were to run the resulting container after I build it, of course, then I can see that those same packages are in my sort of container environment by default. And it's the same versions. In fact, it's the same exact build that was provided by the environment module. Okay, so that was all that. We were working on this basically until Friday at 5 p.m. last week. So there's plenty of future work for us to do. And I think there's a fair bit of work for us to do before we even really invite early users to play with it. But powered by coffee, we plan to do most of these, or tea. So we're interested in doing, you know, obviously validation and benchmarking of the containers for real use cases. Optimize the image size. Spec does a pretty good job of this already, but you know, we think that there are areas that we can improve it further. Automation to regenerate the base image that Mia had talked about after their updates to RPU, so that it's always current. We don't have to do things manually. Handling vendor software is going to be really tricky. This is why we tested this first on our Casper cluster, which is really an open source software stack. Perhaps we'll do like a vendor to open source translation for things like MPI, but TBD. Support for downstream spec instances, which Alex had talked about on Monday. So if there's if like one of our users has installed something in a downstream of spec and it sort of adds on to our software stack, can we incorporate that? I think there's some challenges there, but it seems plausible. Maybe we do add some handling of things like Conda environments, but maybe we just leave that to the user to layer on top if they're so interested. And then, we'd love to provide a platform for building these images so that people don't have to use up all their, upload bandwidth. But, that's also tricky. And then again, documentation, we got to keep ourselves honest on that one and be good stewards of the software. So.
Yeah, just drop a couple conclusions here and thank you all, but yeah, so conclusions here, reproducing an evolving software stack and spec is hard, right? It is exceedingly challenging sometimes, right? And there's a lot of small nuance to go ahead and capture within whatever kind of like, whether it's a container or any other kind of methodology, right? It's tough. Next, assumptions made for managing HPC modules may be at odds with portability. So we came across a ton of different roadblocks here, right? Like just in general at the fundamental like layer of how we set up our stack, which is why we're not like implementing this on our current stack at the moment. It's going to be something that, is going to be in a future stack for people to utilize within Derecho and Casper. And we're looking forward to actually seeing everyone give that a try. Lastly, containerization tools and support are constantly evolving. Like, I think Brian kind of brought this up about spec containerize when we first started working on the project, right? We just started taking a look and trying to like, do some kind of base kind of brainstorming, right? And he saw the changes that ended up happening within spec, right? To like do these kind of containerized functionality, right? And it was substantially more feature filled than it was initially, right? So that kind of enabled us to do all these like nice, cool things. So yeah, feel free to reach out to us if you have any questions. Of course, we're gonna have questions at the end, but if you want to like, come up with something at the end or you just like something pops in your head, feel free to email us at Brian's email here or my email listed down below. Okay. Cool. Thanks so much, everyone, and open for questions.
Thank you, Mia and Brian, for that presentation. Great work, and thanks for making this easier for us. Do you have any questions in the room? Yep.
Okay, there we go. Thanks for the talk. That was really great. And I had a question. Could you elaborate a little bit on how the container, the selection of which container that you're using has gone? Because Docker is like this great base thing that you can build all the other containers from. And it's very useful, but last I recall that you are the super user when you have that, and there's security concerns with actually running applications on the system. And I think you guys listed Apptainer and Charlie Cloud. So are one of those kind of the primary end, container, or are you using Docker? Or just could you elaborate a little bit on that?
Yeah, absolutely. So we're currently using Docker to go ahead and do all these builds. Docker provides a really kind of fundamental stable base, right? We can't run it on HPC, of course, right? But if you're running it on like your local machine or whatnot, right? You can build images pretty easily, right? And it just has a ton of support in the community, just like much larger, especially with Docker Hub, like existing and providing like that nice feature of having like, custom iteration on those containers. So we're starting with that, right, as our kind of base image here. That being said, those images aren't only going to be available for Docker. Apptainer, I believe Charlie Cloud and Podman all have the functionality to run Docker containers or Docker images, right? So, you can basically bring that image to another HPC, right? Run it on an Apptainer system, right? And get a similar kind of like feel, right? And we need to do a little bit of testing to validate this, but that's kind of the idea here, right? Make it portable so you can either bring it to another HPC or run it on your local machine or whatever you really want to do, right? With a nice portable kind of image.
Okay, great, thanks. So you're also using the containers for like your CI testing. Is that, it sounded like you alluded to that, but I just wanted to check.
Yeah, so I think that would be a great thing. I think that would be a great thing for us to do in the future. What we had mentioned in terms of CI was really more, we need to create that base image that then we layer the user's modules on top of. So it would be, I think, a good end goal for us to have like a nice GitHub Actions workflow or something that generates that base image, that builder image when we have updates in our software stack. But we do anticipate, like, when we can generate these containers easily for certain testing use cases, them being pretty useful, or also for our end users to use in CI workflows.
Great, thanks. We've had pretty good success with using containers for CI testing and stuff. And if you want to, discuss it or whatever and everything, I'm completely open, to open up a discussion, and we can kind of share, methods and things like that. That'd be great. All right, thanks.
Yeah, thank you. And let's thank Mia and Brian once more. So next up, we have Simon Boardman, and they're going to be talking about managing a multi-institutional software development project using GitHub.
Hi. So, my name is Simon, and I'm a senior scientific software engineer based in the Met Office back in the UK. I'm the lead
Could you step a
developer.
little closer to the podium,
Oh,
Mike?
sorry.
Thank
Yeah,
you.
I'm quite little. Yeah, so I'm the lead developer on a piece of software that we call Stage. We developed Stage in collaboration with various partner organizations across the globe. And today I'm going to talk about how we manage the development projects despite the very large time differences. Oh, brilliant. That does work. So yeah, here's a quick overview of what I'm going to cover in the next 20 minutes or so. First, I'll give a summary of what the Stage software is. Then I'm going to talk about some of the problems we faced coordinating our development work. After this, I'm going to focus on the key processes we've updated and improved to make things a bit easier for ourselves. Finally, I'll just talk a little bit about future aspirations, because we're looking to constantly evolve our approaches and improve things. And then, yeah, should be time for questions at the end. Yes. As I said earlier, the software that we develop is called Stage, though its full title is the Standard Gridding Engine, which is a bit of a mouthful. Stage is used to standardize data output from various NWP models in various institutions. It's a Python package which makes heavy use of the Iris library for metadata standardization, and NumPy for just a reshaping of the data, basically. We run Stage operationally on our HPC using interdependent cycling task workflows. So at the Met Office, this is using the Silk workflow engine, which is co-developed by ourselves and NIWA. But we also run Stage at ECMWF. There we use ECFlow, which is obviously ECMWF's own cycling software. So yeah, Stage enables the user to make the following standardizations. We have the conversion of model-specific or undesirable file formats into something a bit more user-friendly. At the moment, we're targeting NetCDF across all the different institutions. In the future, there's the chance that we'll go to ZAR as we move to more cloud-based platforms. We have the translation of model-specific metadata to meet the CF metadata standards we decided on ourselves. Next, you're able to restructure data so that rather than having lots of time steps of lots of diagnostics mixed up in single model output files, we transform it so that you get one diagnostic per output file per time period per output file. It just makes it a lot easier for our end users to handle. We also provide the transformation of data from the model output grids to slightly more region specific or even end user specific grids. For example, our UK domain we put onto a Lambert azimuthal equal area grid rather than the standard lat long that comes out of the model. Next, we also have standardization of the set of vertical levels for our multi-level diagnostics. Currently, we handle heights, pressures, and depths. There's also a few diagnostics that come out in different bins that we also sort of smush together. One thing I've not put on there, we also handle ensembles and handling different and sticking all the different members into a single file again, so it makes it a bit easier for the end user to access the data that they want all at once. We also use it to sort of decouple our users from model changes. This is kind of the overarching aim of Stage, so that the model is sort of free to iterate and make quite big changes, but our end users don't have to keep up, particularly when they're dealing with multiple different models. So at the Met Office, we've got, say, 4 or 5 models that we're running, and people might be using information from all of them. And if they're all sort of changing slightly differently, putting the data through Stage means that the data coming out of our global deterministic model is pretty comparable in shape and metadata to what's coming out of our UK ensemble. Yes, a bit about our collaboration. The Met Office jointly develops the Stage library codebase with 3 partner organizations. We have the Bureau of is there a pointer? Oh yeah, there we go. We have the Bureau of Meteorology in Australia, we have Met Service Singapore, and we have Lincoln Lab, MIT over here in the States. So we have 4 sets of developers in these locations, and there's a maximum time difference of about, I think it's 16 hours between the east coast of the States and Melbourne down in Australia. I think that's right. So yeah, this makes meeting for discussions about planning the project and who's working on what all at once quite challenging. Basically, we'd need someone needs to be up in the middle of the night, which is not ideal. Or alternatively, it's getting a lot of expensive travel funded. We have had workshops normally at the Met Office, I think twice in the past 3 or 4 years. So yeah, it's quite a rare occurrence where we're all in the same room, even virtually. Oh no, that one. There we go. We do have weekly stand-ups to try and maintain a bit of direct contact, but we have them sort of rationalized so that you kind of got your nearest geographical partners talking together. It's like a big game of telephone at times. For our meeting with our colleagues in Lincoln Labs in Boston, the time difference is quite reasonable. But for the Met Office meeting with our colleagues at the Bureau, it's quite difficult. It's very much at the limits of our workday. In fact, we've just switched to daylight savings time, which does make it a little bit better. Now it's 8 AM our time and only 5 PM Melbourne time, so it's just about tolerable. So yeah, it's just something that we're constantly refining and trying to tweak. And so whilst we get quite a lot of value out of the weekly stand-ups, there's a lot of other stuff that we do to sort of streamline this approach, and that's what I'm going to cover in the rest of the talk. So yes, since getting everyone together is quite challenging, we've been utilizing asynchronous communication methods in addition to these stand-up meetings. So the lowest friction tool we had available is email. And using an existing tool that everybody was familiar with kind of made a lot of sense to start with. We found it very easy to send lots of information about the project, no matter what time of day it was, and it didn't matter if people weren't replying instantly. So that was quite nice. However, we started to run into problems when the project team sort of changed composition. People joining, people leaving, it became a bit of a nightmare. Having an up-to-date email list was just a real challenge, and nobody quite managed to own it, particularly being spread across 4 different institutions. It's not great. We were also quite worried about losing information in people's email inboxes, people not spotting emails, or if people are leaving or joining, it's very difficult to fill new joiners in on information, or if people leave, then when inboxes get closed down and deleted, there's a real risk that information could disappear. So whilst we liked the asynchronous aspects of email, we thought that we could do better using a different tool. So we considered a few different options. There's the same style of asynchronous communication, including SharePoint, Jira, and GitLab. However, we settled on GitHub mainly. since we use it already for the code distribution, and the Met Office also has an enterprise account, which allowed us to use a lot of extra features. Just the easiest one, really. But using GitHub for sharing communication, code, and documentation means that the account management is really simple. All we need to do is add people to the right repository. We don't have to faff around getting things set up, different services. That's a big plus. Centralizing our communication on GitHub also meant that anyone could log in from anywhere in the world, and they can access a single canonical source of information and discussions all about the project. And the main downsides we've found is that it's quite tricky sensibly collating information when you're working on multiple repositories. I'll go into that in a little bit more detail later. It requires a bit of effort to put things into a sensible structure, so it's not an insurmountable challenge. In addition, at the moment, our project is closed source, so new developers on the project do need to be added to the Met Office organization, but it's a fairly low overhead. So yeah, I've broken down types of processes that we want to improve using GitHub into the following sections. Planning what work needs doing, when it needs doing, and who is doing said work, so that we're delivering the right thing at the right time. Reporting on the status of work, so we know when to expect review requests or additions to the main code base. Testing and reviewing work prior to completion to ensure that proposed changes meet the agreed standards and technical requirements. And finally, documenting these changes to inform users and developers what is present in the code base and to make sure that our design decisions have been recorded somewhere. So, with a wide array of developers working on different priorities for different organizations, we wanted to make it easy for everyone to coordinate work. We need to be able to capture work that needs doing and identify shared requirements. Having work that benefits multiple organizations helps us prioritize these things for development and inclusion in our next release. We also want to be really clear if there are specific time-bound deadlines for different bits of work that need to be completed. Finally, working out who is going to do the work is really important, so we don't have any sort of duplicated effort or conflicting solutions being developed at the same time. Like many people, we're using issues to start to capture information about work that needs to be done and bugs that needs to be fixed. So in these, developers describe the work that needs doing in an issue and then apply various bits of metadata, which I'm showing on the right-hand side here. And the metadata is really, really important. It helps us organize these tickets and sort of put things into a sensible structure. In addition, the full text search that GitHub has is pretty powerful and makes it really easy to see if someone else has seen your bug, or if your great idea for a feature has already been written up. And at least you can then plus one it and say it's important, which is quite nice. So each issue uses labels to describe the type of work, and then we also use milestones to target specific releases. This also gives an indication of sort of the timeliness of the request. So yes. When issues have milestones attached, it allows us to look at whether we're ready to do a release or not. We need to know if the stuff that we want to send out into the world is ready or not. And this gives a really nice, quick, easy way of looking at it. Here you can see we've got 2 issues that need to be closed before we can cut our 2024.3.0 release of the stage library code. So it just gives a nice, clear indication of what work needs doing, and allows us to move tasks around into other releases if we have some sort of time-critical component that has been completed, and there's still stuff. And if there's still other stuff that we'd like to do, we can always shunt it to a different release and know about it really easily and not lose it. Yes, we're quite busy now. It's big. So yeah, like I said, we develop across multiple repositories for different aspects of the stage project. These include the shared library code, which is the main focus of this talk, but we also have our model-specific processing configurations and also workflows that we use to run these operations. These latter two are a bit more organization-specific, so whilst they don't get co-developed, they do get shared for reference and sort of starting points for new members of the team. To organize this work, we've started to make really good use of GitHub projects. This is what I'm showing you here. And this allows us to arrange the issues and PRs in various views from various repositories, in fact, to accurately identify what work is currently in progress, what's been completed, and if anything is blocked as well. It looks like a lot of ticket organization software, course, but having it baked in next to where we're doing all our other bits of development is very useful for us. So we don't have to worry about linking other tools and sorting multiple accounts. So it's just nice and easy, really. Path of least resistance sort of thing. GitHub projects allows you to configure a whole range of views. I think it's still it's quite new, really. And even in the course of us using it, they've added in lots of different things. So our main view that we use is this Kanban style board. We actually use this like slimmed down version, really, that just has the blocked in progress and in review, and use the backlog when we're talking with our product owner about longer range time planning. So yeah, we refer to it almost daily for status updates in stand-ups, in our local stand-ups, and then share it a bit more widely in our stand-ups with our collaborators. We're also starting to make use of the newer features for time and effort estimation. There's a really nice proper time back, what they call. There's a really nice view that'll give you a Gantt chart. There we go. So you've got an idea of what's overlapping, but we haven't set it up yet because it requires adding estimates to everything, which is a slightly daunting prospect that we haven't really done before. But yes, there's loads of new stuff that we're hoping to take advantage of. There we go. Oh no, I need to go back. Yep, sorry. We developed, like I said, we've developed a series of different views to organize issues and pull requests according to theme. This means it's really easy to monitor progress with respect to certain goals. So here we've got all the issues and pull requests that are specifically related to ECMWF work. Here we've got everything pulled together using the ECMWF label. So this encompasses 3 separate repositories again, but we've got them all here on one board. So it's nice and easy to look at, and I don't have to go and chase around 3 different repos and look at the issues in one and the PRs in another. And yeah, so it's lots better. Yeah. Reviewing and checking things is obviously a very important part of any sort of software project. And then for small changes, we tend to just ask for reviews for with developers locally. So I'd ask my colleagues in the Met Office and tend to get a review the same day, which is quite nice. However, there are cases where there are much larger changes with more significant impacts for the software. So in those cases, we explicitly ask for reviews from all the partner institutions. Yeah, so working across lots of time zones can occasionally make it a bit challenging if you've gone to something that will impact everyone, but it looks at quite trivially. You've got to sort of wait for the next day and everything, which is a bit of a pain. However, there are advantages. I can submit a PR at 5 p.m. and log off, and then by the time I've logged in at 8 a.m. the next day, my colleagues in Australia have probably already looked at it, which is actually quite nice in a way. So yeah. With reviewing, we really want everything to be focused on the code quality as much as possible, the thing that has a real impact on running the code and using the code. So there are several things that we do to streamline this process and try and make reviewing a pretty low friction activity. I'm sure that I don't need to inform you of all these things, but we use a fairly standard set of tools to set the style and formatting for the library code. We have a GitHub Actions workflow set up to run these style checks on every PR. This means it's really quick and easy for both the submitter and the reviewer to see if the proposed changes meet the required standards without having to check out the code itself. To further aid developers, we also have the configuration for these tools stored within the repository, and also make use of a pre-commit hook. So this automatically applies any of the required style changes during every Git commit. So again, all low friction stuff, automate it as much as you can, make it really easy. In addition, we also run a tool called Bandit, which checks for common security issues within the code. So this is particularly important for us because basically all of us are government organizations, really, and security is obviously paramount. We've found that this combination of GitHub Actions and the local pre-commit hook makes that actually by the time a reviewer needs to look at the code to review it, they're literally commenting on the functionality and the quality of the code itself. They're not having to muck around with, well, you've messed up your indentation. Why is this variable not named correctly? Sort of thing. So it's really decreased sort of like the turnaround time for reviews as well. It's helped us iterate a lot quicker. Like many of you, as part of our review process, we make use of unit tests to vet the functionality of the code. One of the key things that we want to ensure is that the code changes in any PR are going to be okay running in any of the operational environments of any of the organizations. So these environments get managed in different ways. Our MetaFist machines use centrally managed environments, as do some of the Bureau machines, but then others use Conda environments. Both Boston and Singapore are running in their own Conda environments. So when we make the code changes, we want to make sure that everything still works basically in these quite tightly defined environments. So one thing we could do is follow the process in this flowchart, where if we've got there's a new review required, and each of the organizations have to check out the code on their local machines and run that changed code in their organization, in their exact organizational environment, before they send things for feedback or if notifying of test failures and everything. But it would mean everybody doing it, and with the time zone thing, it's yeah, it'd be a pain. I mean, of course, there's a very obvious solution to this. So to prevent this bottleneck, we recreate all the environments using Conda. We've nailed it down to certain key components, and we run the tests in each of these environments remotely using GitHub Actions, and we can do this in parallel, which is quite nice with the matrix running in GitHub Actions. This gives developers pretty much instant feedback on whether they're making or accidentally making breaking changes in environments that aren't their own. So it's just a lot quicker. You get a lot of much quicker turnaround. And again, it means when your reviewer in a different organization comes to look at the code, they can look at the quality of the code rather than worrying about does it run on my machine or not. So yeah, it's quite nice. Like I said, with a large number of distributed developers, it can be quite challenging to keep track of the code changes over time. So to make it easier to identify these impactful changes, we started doing proper releases on GitHub and actually making change logs. It sounds really obvious, but yeah. So we started out using the GitHub provided change logs, the release notes really. However, as you can see, there's just a list of pull requests basically, and you can't really tell, but like, are these impactful? How much are these going to matter to me? You know, what sort of changes are these? So we wanted to improve that and make things a lot easier for people. So we considered sort of splitting things up manually, going through, putting things into sections, but we eventually found a tool to do it. So it was a lot easier. So there's a tool called Town Crier, and this partly at least automates the process. So to use Town Crier, every pull request needs to include one or more fragment files in addition to the code changes. Each fragment is a plain text file where you put, well, they're up there. You put a little description in, and the fragment file is named after you've got the issue or the PR number as the file name, and then you've got the type of change, or well, a key for the type of change as its file extension. So here we've got changes. One's a feature change, one's a miscellaneous change, and one is a bug fix change. I've got the bog standard or the default sections on the left-hand side of the slide there, but it is possible to write your own custom sections, which we do for our configuration repositories, which is really useful for talking about which diagnostics have changed and which have been deprecated, that sort of thing. So when we're ready to do a release, we run Town Crier, and this converts all those fragment files to our nicely formatted changelog, what you can see on the left here. There you go. This file then goes into our main documentation and makes it really easy for users to be able to work out what's been changed, well, what exactly has been changed between releases. The most important thing is that we don't have anything on there at the moment on that one, but you can see what's been removed, which is always really key, what's been deprecated, rather than getting a new release and going, oh gosh, where's that gone? To check that each PR includes a fragment, we use yet another GitHub Actions workflow that runs Town Crier and does a check. And here we can see that it's running and it finds this file here, the 720.misc file, and so it's happy and it passes. If we didn't have a fragment file, it would fail angrily until the user fixed it. As well as our changelog, we of course have written pretty in-depth documentation about the code itself. This again, all jointly developed with our collaborators. Anyone working on the code base is encouraged to contribute to it. The documentation includes a user guide for people wanting to run stage on their data, a developer guide for people wanting to contribute to the project, and an API reference documentation describing the individual components of the code base in quite a bit more detail. The aim is that anyone using or developing the code base has a single canonical source of information, reference source, and having it stored in the GitHub repository itself makes it very easy to link it to the link it back to the code, and when people are submitting PRs, it's obviously very easy to point out, have you updated the documentation about this? Easy to see that. So yeah, like many people, we write the docs in restructured text, and then publish it using GitHub Actions to GitHub Pages, which runs Sphinx. For every PR, we also have an automated check to ensure that the documentation still builds successfully. Sphinx is a bit pernickety. Again, instead of everybody having to check out the code, check it builds, etc., it's much easier to just automate it and make GitHub Actions do it. Again, this still reduces our review time and complexity and allows the reviewers to focus on sort of the content changes rather than sort of the technical will it build or not. Finally, I'd like to touch on a couple of bits of work that I plan to do in the future to make contributing to the project again just continually easier and make it better for people to be engaged. So one of the things I want to do is improve how we capture sort of the less formal bits of the project. By the time something's got to an issue or a pull request or anything, it's sort of quite tightly defined. But what we're not great at capturing is sort of the start of that of all that, sort of the ideas. And so I recently started setting up GitHub discussions, which it's sort of like a message board, sort of like a forum, maybe. I'll have describes. I'd call it relaxed issues, and they're much more conversational. So what we've done is sort of get something that everyone can contribute to, make it really easy to have it persist as well, so that if people are moving from the project, you can still see what they've done. Makes it really easy for new developers to come on board and sort of have that audit trail. They can go back and read what's already been done and work out what's going on. It's quite nice. And then once we've sort of hammered something out and got a more concrete proposal, GitHub gives you a little button to automatically convert things into a full issue itself. So then again, you've got it on the board, it goes into the normal workflow process, but then you've still got a full audit trail. So yeah, that's quite nice for documenting your design decisions. Oh yes, and the other thing that I really wanted to improve was that we're not very good at communicating upcoming changes to our users. I showed you that nice changelog, which is great. If you're using a built version of Stage, that's fine. However, if you want to know what's coming next, there's no real way to do it other than dig around in the fragments that still exist in the fragments folder. This is not really ideal. So I want to update the GitHub Actions to build a draft of that, build a draft of the changelog and have that kind of update when every PR gets merged into master. So yeah, it's another little thing I'd like to do to make things a bit better. So yes, finally, I'd just like to take the opportunity to thank all our collaborators, particularly my colleagues at the Met Office who've reviewed this presentation, but also yes, Daniel, Tim, and Robert have also been the leads at their organisation and have made significant contributions to the project as well. Oh, that's not formatted very well. I was meant to say Q&A. I'm going to stick it back on that one. So yes, if there's any questions, chat.
Yeah, thanks, Simon, for the great overview of the project management and developer tools and GitHubs. There was a lot of good nuggets in there. So thanks for sharing what's helpful for your team.
It is good. It's very useful.
And a couple questions. Yep.
Yeah, hi. Great talk. I was just curious what the and maybe I missed it. I apologize. What's your actual Git workflow? Like, it sounds like at the very end you mentioned master. Does like everything go into master? Do you have like a develop branch? Are there feature branches?
I think we're broadly, I can't remember, I can't quite remember which one it is. We are broadly using Git flow. We tend to, releases come off master. We do use feature branches for longer running, more complicated changes, but in general, small PRs target master, and then we release, tag and release off master. That's generally how it works. It's still, again, it still is evolving. We're quite pragmatic about it. The development teams aren't massive. There's 7 names on there plus myself, and that realistically there's about 10 people at the moment. So it's kind of quite easy to do ad hoc. Yeah, we're quite pragmatic. We try and make it simple and maintainable, rather than bogging ourselves down and going, well, we have to do it this way. Yeah, we're flexible where possible. But yeah, good question.
So one of the challenges we have with the SPAC Stack collaboration is that all of our participant agencies, we all have slightly different interests. We have different platforms we care about, different subsets of the packages. So I'm curious, how do you handle, or, how do you sort of prevent a situation where, the code that I push, maybe it works great for my use case, but then I end up sort of stepping on a few other people's toes, whether it's automated solutions or just kind of communication logistics. How do you handle that?
So it's a bit of both. Like I said, we had the actions where we're running in those different environments. So it'll flag up if there's a problem running in those environments, and then it's generally collaboration via PRs are going, this doesn't work for us. Can you change it to this? But not being dogmatic about it. We recognise that in general, everyone is working together. I think it does possibly help the Bureau and ourselves at Met Office, probably the main 2 organisations leading the development work. Most of the contributions do come from the Met Office side. It is that. And that's where those weekly stand-ups come in as well. We're making these changes. They're going to impact you. What do you think? We can at least have a 5 to 10 minute conversation about it to sort of flag up things that might be a problem.
Thanks.
And then we have one question online there too, and if you can read it.
Oh, I can. So Nick Kedzuf has asked, how is the responsibility for GitHub logistics, i.e. maintenance of the actions ecosystem, projects configuration, etc., distributed or not across the teams? Is it everyone's responsibility? Is one developer the GitHub person? Do you have a DevOps engineer? Good question. It's probably it's mostly led by myself, as sort of the senior engineer on the project. But again, we try and review our working practices fairly regularly and sort of make sure that things continue to make sense to everyone. So we do try and be collaborative, but
I work on a verification software where we collaborate with the Bureau of Meteorology and also the Met Office. I'm excited to see the same sort of setup that we use. One part we're not using that you mentioned is the pre-commit hook.
Pre-commit hook. Yeah.
And it sounds like that's used in forced coding standards. Can you talk a little bit more about that? Is that run locally or is that run through GitHub Actions?
Both. So we have the configuration for the pre-commit hook stored in the repository, and then developers are encouraged, but you don't have to have it installed locally in the development Conda environment that we also supply. If you've got that set up, which I do because it just makes my life an awful lot easier, when you write your git commit message before the commit gets sort of signed, it goes through and at the moment it runs black, it runs flake8, and isort, a few other sorts of things like fixing up line spacing, etc. We do want to transition to rough at some point because it's quicker and easier, but we haven't got around to that yet. But then when we push to a PR as part of the actions workflow, it also gets run as a check again, so that people who haven't installed the pre-commit hook have the same changes applied. We do it as a check, and that if the tools can't run, or if they have exit statuses of 1, they haven't worked, then the actions fail. There are people who just have the standards applied automatically and new commits added on GitHub, so you can do it in a couple of different ways.
So it actually changes the lines of code
Yep.
for you.
Yeah, so
That's awesome.
yeah, it's really, really nice.
Great.
It just saves us so much time arguing about style pointlessly.
Okay, let's thank Simon once more. And we're on break now, and we'll reconvene again at 11 p.m. or a.m., sorry. Mountain time. I need some coffee. So see you again.
Check, check. 1, 2, check. Check, check. Check, check.
Okay, we're gonna go ahead and get started up again. Oh, wait 1 minute. Okay, we're gonna start in 2 minutes, false alarm. Okay, another false alarm, just a 1 minute break there. So we're gonna go ahead and restart. First off, after the break, we have Anthony Islas talking about the importance of reproducible local testing.
Thank you. Are we good to go?
Yep.
Awesome. All right. So I'll be talking about the importance of reproducible local testing and mostly hoping to spark a discussion about modern testing practices and what I've observed in industry as well as here at NCAR. And first, we'll be exploring some scenarios about projects' natural progression into the testing environment, as well as some pros and cons of testing directly in the CI/CD environment. And you're going to hear me say CI/CD a lot. It might get a little overwhelming. And then talk about how testing actually differs from CI/CD, and then the intermediary layers of reproducible testing as they resolve into dependency solving and testing procedure itself, and how we might be better across the board in our projects about separating out testing from more complex non-local frameworks that don't provide that solution. So first things first, let's explore a scenario about a project's testing progression with regards to a project started before CI/CD being widely accessible within the respective hosting platform. So I'm talking about the days of Synergy or SVN and things like that. So say we have Devin, Dev for short, comes in and makes a contribution. And naturally, hopefully, they write some tests along the way for their contribution as they're developing, and they can run these locally. Likewise, if you have a local other tester, someone else on your team or someone who wants to adopt this, they can go and run your same um, local tests, functions, scripts as whatever you have it. And as you're making these contributions, you go in, you maybe have a review for the commits and you go run it, or you have some sort of honor code system where you say, yes, I did run the test, everything worked out fine. But this starts to get a little tedious. You make contributions and then you find that the actual contributions themselves down the line maybe broke something. Maybe they were testing out for specifically their changes, but it broke something else down the line. Classic regression test breaking. So what you do is instead is you start to maybe automate this a little bit. You start to introduce maybe a cron job, and you wrap these around. You run it on someone's machine. The machine's always up, and it runs in some environment akin to a local test, and that's fine because our local tester here is still able to run these tests. However, naturally, you want to know when these tests actually fail. So you, of course, have a mailing list, and when things break, you send that out to the devs team and anyone else, and everyone gets happy, when things don't break or do break. I like to find when things break, so that makes me happy. And naturally, this still works because, again, our local tester is still able to run the tests. They're basically one and the same, what's running on the cron job and what is the local tester actually running. But again, this is only running on a very time-based measure, some sort of frequency with the cron job, nightly, weekly, whatever you have it. You still require that people run their tests whenever they're making contributions. And it would be really nice to have this with the advent of CI/CD and integrated cloud solutions to have this already run right then and there. So that way, whenever people make contributions, you check it on the code they're actually running. No more sort of honor system. You make it an objective uh, checking of all the tests actually running. So you replace the cron job with some sort of cloud or CI/CD platform or system, and this will run the tests. And this is great. However, as you start to develop more and more contributions, maybe it starts to get a little more tedious, or you want to write the test directly in there. You start to take on the nuances of that actual hosting platform. Maybe you have to set up data in a particular way, or you're running a test matrix and it's much easier to just write the logic of how to do that, or any parameters that you're using to launch your Google tests. And you start to write those specific to your environment. And soon enough, the actual realm of your test starts to live primarily within your CI/CD solution. And this seems great. These are the tests that you're running to check to make sure everyone's doing everything correctly. But the specifics of it introduce a new problem. Our local tester can no longer actually test the code directly. And that's not to say they can't just go and look at the code, look at what's actually running, and replicate it themselves. And you might say that's fine. They'll just go and look at the code that's being run on the CI/CD solution and then run it themselves. It's self-documenting. But I pose to you that that's the same equivalent of saying, well, you don't need any sort of documentation or read the docs, Doxygen generated HTML web pages. You can just have a user go in and read the source code. It's self-documenting. You can just do that, right? Um, and you might see that's not really ideal. You want a way for people to easily access and run these tests. And so with our local tester not being able to actually run these tests, if they start to introduce very specific things to the CI/CD environment, we now maybe do that sort of duplication. And this duplication of the environments or the tests themselves are often either one-off or only known by people who have written those tests themselves, so experienced developers or people who were there before the actual transition to a full CI/CD solution. So now our local tester can actually run these, but inherently, because the CI/CD hosted tests are the definition of what's actually being run, these one-off solutions are unofficial. And as the name implies, because these are unofficial, the CI/CD hosted tests, those definitions are the official tests. And again, this might seem fine. Okay, maybe to run a local test, you need to have just the knowledge or talk to someone who knows how to set it up to do all that. But now you have a new dev. They come along. They also make a contribution. And it's a lot of effort for them to maybe go talk, figure out how to do all the unofficial testing, run it locally if there's not an available entry point. So rather than that, we have this ease of automation of, making a commit and the tests all go run. They are the official test of what makes sure that things actually go in. So we'll do exactly that. New dev will come in, make a commit, and we'll get some response back, run the test, and it comes back and maybe things break. We get some log files, things didn't work out well, and then the new dev will again just make some changes and commit again. And maybe things break further down the line. We got a little further, and so error logs come back, and we get into the cycle actually, where this new developer, through the ease of just committing and making the CI trigger, we are now into this sort of development cycle where we're using the regression CI tests as a way to do local development. And I pose that this is actually not a great development practice especially when your solution, your software is meant to be running locally. If they are developing local contributions and testing things and the software is meant to be locally, they should be testing locally as well in their everyday to day contribution and development. So now we'll take a look at where a hosting platform starts with CI/CD already part of it. And we see a similar story. Again, it doesn't always follow this way, but in my experience, speaking anecdotally, this is something that you can fall into, where again, you have a developer comes in.
I think we lost Anthony.
Hello?
Okay, Anthony, we have you back. You can reshare.
Yeah, I will go ahead and share that again. Sorry about that. I have no clue what happened. Let's do the entire screen. Okay, I don't know at what point it cut off, but we will continue. All right, so in the instance where we have a project already having CI/CD, we start to see that we might also make a contribution, already have a hosting platform, make our tests. The tests are directly hosted within that, so we start to write our tests specific to that environment. And we might, still have our mailing list or whoever's part of the project. We send the information out to them. Our local tester still can't run these tests. We have this set of unofficial tests that come in to play, and we might end up having these same patterns. Again, this isn't something that always happens, but is a development practice that I see can occur, and I have seen it occur a number of times. So writing tests inside a CI/CD framework can actually lead to detrimental development practices, in my opinion. So what I want to kind of go over now is the pros and cons of testing directly within a CI/CD environment. And what I mean by directly is, again, writing any substantial amount of our testing logic within that CI/CD framework, not just your entry point for your C test or things like that. So pros, again, it's all about automation, reducing the workload of common tasks. It's tried and true is you should be using it. It's incredibly feature rich and has a lot of options that we can leverage, as well as able to quickly integrate with external tools, make our lives a lot easier. We'll always be running in a stable environment with high availability. We're always going to be testing to a specific SHA, so that way whenever we make a commit, a PR, it will be testing specific to that. And because our tests are hosted directly in there, the tests are always one-to-one. We know we're running the tests. They're not on, a stale version of our master or our trunk. The tests are going to be specific to that actual commit. Now for some cons. We have some syntax and language specifics. And so you might be running with the nth flavor of YAML or an actual specific language to the tooling. The error output is always going to be static. This is inherently just the nature of logs. You won't be able to actually go in, attach a debugger. All the features are not universal. Similar to syntax and language specifics, things might differ between platforms, and so a shift in platforms will be very painful if you write a lot of your stuff specific to the platform. And you try to avoid it, but sometimes that's unavoidable in terms of switching platform. Inherently, you can't account for all user environments. We'll see how we can sort of handle that, but especially if your code is not meant to run within a Docker or container environment, you start to run into an issue where if you're running bare metal, you have it on people's different machines, you simply cannot account for all the various multitude ways that people set up their environments. All of this together, again, as we saw with the example, I don't know if it cut out, but this can lead to abstracting the test to become too specific to the CI/CD environment and write things that are part of or using features of that environment itself. Again, this can lead to poor development practices. And at the end, we almost have no support for local runs. Again, we simply cannot take those tests verbatim and run them with an easy method without going and inspecting the actual configs themselves. And so what I want to get at is that automated testing is meant to catch when the errors occur, but it shouldn't be part of your everyday debugging tool if you're developing locally. And so the ways in which testing differs from CI/CD, what I want to drive home is the point that tests are unto themselves an absolutely critical and essential part of software development that are independent of CI/CD. And we'll get into what I mean by independent, because you might say, well, no, they're kind of intertwined. And local testing is, or rather should be, the progenitor of these CI/CD hosted testing definitions. In the scenarios that I went over, again, I don't know if they cut out, we have testing that was written originally in a local environment. And you can totally have tests before you have CID. That's the way it was before CI/CD became widely popular. You can't have it the other way around. And so our tests should always be able to run at least locally, assuming you don't have to have it in a particular environment like a cloud infrastructure. And so CI/CD and testing are not the same thing. It's the automation of testing, or better, CI/CD is the automation of your test, where the implication is that these tests can be run in a non-local manner. And so what we might want to do instead is aggregate them in some manner to facilitate running them, where it's still usable by our environment, but also can run outside of the environment. And I'll call this thing an aggregator. And so regardless of where you're coming in from, the commands are more or less the same, and the user will be faced with the same way that the CI/CD environment will be running them. And so at its core, CI/CD is the automation of these common processes, but not the processes themselves. And so now what I want to go into is separating this out into definable intermediary layers of reproducible testing, and how CI/CD isn't the solution for reproducible testing, it rather builds upon them. And so, not to surprise anyone, the two different definable layers are dependency solving, i.e. containers, or just setting up your environment, and some sort of testing procedure, workflow manager or aggregator. And so looking at the pro side, when we run in a stable environment, this can easily be solved by containers. We should be using containers or some sort of stable environment, and this is often built into CI/CD frameworks, but isn't necessarily an inherent pro or feature specific to those environments. And so we'll knock that out. Excuse me. And testing always one-to-one. Again, if we make our testing procedure the way in which we set up our tests, setting up paths, setting up data, the order of operations for our tests, if we define that into a separate layer that always runs in that way, that's not inherently part of our framework. So we can get rid of that. Testing always specific to a SHA. Well, this is actually really a pro of the framework. This is more of a pro of good testing practices, of keeping your tests version controlled along with your code. Don't keep your code in a different folder, in a nightly folder outside of your trunk if you're using SVN. Don't keep your test code in a different repository. Just keep it with your tests. So this is inherently not necessarily a pro of CI/CD frameworks. And we start to see that on the pro side, now we have a reduced workload, feature-rich, and quickly integrated. We're working with common or the core actual benefits of these frameworks. And on the con side, we can't account for all of user environments. This can partially be solved, again, by dependency solving. It's totally not even a question if you're only working out of a containerized solution. But if you're actually planning to run bare metal again, or account for all of different people's ways they want to run, having a testing procedure workflow that always runs the same way helps alleviate this a little bit, because while you won't be able to reproduce that user's environment, you will at least allow them to run the code, the test, in the manner that you would normally run them, at least in terms of the procedure. And so we'll introduce a little icon here with grayed out text, or grayed out background, strike through text, and dashed lines, which is a mitigated con. We can't quite solve it entirely, but we've at least mitigated the cons of this. And so accounting for all user environments, we partially solve this. Likewise, the error output being static, testing one-to-one, if we're able to reproduce this test, sure, the error output is always going to inherently be static from log files, but because we can go and see what failed and then run the exact same code verbatim in the proper order that it was set to, the testing procedure slightly mitigates this. Almost no support for local runs. Again, if we're able to run this locally, that's just not much, that point is moot. Again, in the same manner, route to abstract tests from specific CI/CDs, because we've separated out into a definable layer that has nothing to do with that framework, that is also not an issue. And those two together all are what lead to some of the poor development practices that I've talked about. And you can still have poor development practices without or having solved all these. So we didn't totally solve that, but we've at least mitigated the portion that I've talked about. So that's been slightly mitigated. And so when we get rid of all that, when we get rid of all, the issues that we've seen, we balance our pros with the cons of the syntax, language specifics, and not all features universal. We start to see that balancing our CI/CD framework and using it in its strengths and weaknesses, balancing those are a lot easier when we have the rest of everything else that we're looking for separate it out into other layers where those should be solving those issues. And so a do-it-all solution can work for people, and if it works for you, and that's fine. But as solutions and software gets more complicated and has more ways of running, it starts to introduce unnecessary limitations. And so when we look at those definable layers, we actually see that testing has no requirement of CI/CD specifically. We can run tests outside of that. Whether it's dependency solving, again, using containers, we have Docker, ECS, Kubernetes, Apptainer, Podman. When we start to look at generic testing procedures, we have maybe Earthly, Bazel, C-test. I'm sure there are more, but the test isn't as extensive. And when I'm saying aggregators, I'm actually deliberately not including, again, CI/CD solutions, so not Travis, not Circle CI, and not exclusive unit testing frameworks like Google Test, PyTest, JUnit. And you might say, well, you can totally use PyTest to go and invoke other tests, and you can push software to just do system calls and things like that. But we're looking for something that's more generalized in using those, because often those are used specifically just for language-specific unit testing. So if a project wants to use these sort of test aggregators or workflow managers to wrangle multiple types of test entry points, the options are somewhat limited. And so what I want to get at is you want to have some sort of tool or aggregator that facilitates these tests in a simple way, such that a local tester or in any other environment, the way you interact with it is the same. And taking an example like Earthly, it runs in a containerized environment. Again, if you're running in a containerized environment and that's the way you prescribe users should use it, this is not really much of an issue. But if you're planning on running in local environments or accounting for people's various environments, this simply doesn't work anymore. You won't be able to have local runs because this requires a containerized environment. Things like C-test and Bazel maybe account for that a little more and aren't dependent on your environment, but now have heavy-handed syntax and language specifics. We want it to be very easy for people, especially in community-driven models, to be able to add and modify and look at what tests are actually doing. So while a one-stop shop is nice, it starts to reduce maintainability. As we've seen in software development over the years, software compartmentalization to smaller pieces actually makes it a lot more maintainable, more robust, and able to take those small pieces and apply them to a wider problem space. So I pose an alternative, and I'm going to add HPC systems into this alternative just because a lot of the systems that we use often make use of HPC systems. So the aim is to have this tool that is able to be used in HPC systems, bare metal, CI/CD, containerized environment. Basically, it doesn't kind of care about what the environment is. We're just looking for some sort of intermediary layer to facilitate testing procedure. So our objectives. It has to have a simple interface, easy for new users to add tests. It's able to run in the HPC environment, but isn't specific to it. It should be able to run in any sort of environment. It's not dependent on any external packages or tools. This is kind of a just ease of use sort of thing, because we already have another layer that's solving dependencies. We don't want to add to that problem. And we can accommodate multiple testing styles, again, whether we're using Google Test, C-test, bash scripts, things like that. And I find that this concept is actually very simple. And I think sometimes it's actually so simple that it's actually overlooked as a formalized layer in testing, in the same way that I think we had a presentation on Monday about the unified workflow framework. And I think they made a great point that this sort of thing is often simple, but without it, you can often have brittle procedural code that is just so project specific and one-off. And so rather than having just scripts that go and say, this is what you do all the time, it's just a shell script. I likewise have a proposed solution, which I called HPC Workflows. It's, again, just a Python-based solution that has no other dependencies and operates on a small number of requirements. I won't go into those, but if we have time, we can certainly explore those, or if people have questions. As an example, on the left, we have our most basic example where we just have tests, steps, and it's in JSON, so we can just see that there is a command script. It can be any sort of executable, and we have some arguments. On the right side, it's a little more in-depth, where this is actually a compilation test for WRF itself, where we have accounted for various HPC options where we're running onto Retro, and we're testing out compilation with GNU. And you might say, well, I thought this was not supposed to really handle environments, and in reality, it doesn't. The framework itself doesn't care about environments, but is flexible enough to allow me to add various ways to specify what modules I'm going to want in my test. And then in my actual build.sh script, whatever arguments I get passed in, it's on me, the test writer, to figure out how I want to handle my environment, whether I use a container or not. In this case, I've just chosen for my build.sh script to ingest arguments and load those as modules. And I guess the takeaway here is that using frameworks either like the one I've written here and proposed, or things like the unified workflow framework are excellent solutions to provide an intermediary layer in testing, and you should consider those when developing complex workflows and make sure that a user is able to run things locally, even when you're testing in a CI/CD solution. And that is it. Thank you.
Thank you, Anthony. Do we have any questions in the room? And just a reminder, those online, please go ahead and enter your questions into Slido. Not seeing any questions from the room. Did you have anything extra you wanted to show us, Anthony? I know you mentioned a couple things. We have a couple minutes.
Yeah, I mean, if I do have some extra time, is my screen still being shared?
No.
Okay. Wow. Okay. Again, I think just taking a quick look at the GitHub itself, a lot of what I've worked on.
We don't see your screen. It's blank at the moment.
Oh, probably because I changed tabs. That's fun. Okay. Yeah, a lot of what I've written for this has been over the years an iteration on a. Is it showing now?
So that's probably my fault for putting you on the spot, though. Live demos never work. I'm sorry.
Yeah, well, that's fine.
It just showed up.
Okay. Yeah, a lot of what I've worked on has, over the years, been a refinement of a system to generalize, submitting to various HPC systems, as well as provide a generalized workflow. But I think the presentation that was done on Monday was also very good as far as having a generalized workflow to facilitate testing. In my case, I really wanted to solve an ability to run an HPC system without having to constantly write PBS or Slurm scripts. And the way it operates is more or less explained in just a few paragraphs and steps. And with this single paragraph or chunk here, that's the majority of how this framework operates, in an effort to make it very approachable and easy to adopt with no extra rules. But I think we're up on time, so I think that will be about it for me.
That was very cool. Thanks, Anthony, and thanks for being a good sport about that. Let's thank Anthony one more time.
Thank you.
And for our last talk before lunch, appropriately, we have a talk about noodles by Nicholas Brunhart-Lupo.
Harry, all right. Hello. Thanks very much for for listening to my talk here. My name is Brunhart-Lupo. I'm a senior scientist at the National Renewable Energy Laboratory, which is just down the hill. I recognize that I'm all that's standing between you folks and lunch, so I'm going to try to be quick and make this entertaining. So let's see if I can get this to work here. Go that way. All right. So this whole noodles thing kind of sounds really weird. So let me just start with some context. We're facing a lot of challenges at NREL when it comes to visualization and analysis, and I don't think our problems are particularly unique. I think it's fairly common across the whole industry. We have these data products that are just getting larger and larger. We're talking about multi-petabyte size data sets. We have the problem that these data sets are getting more complex inside them. We're talking about more tortuous data sets, more interesting features inside them that are hard to kind of tease out. Our teams are getting a lot more diverse. And I don't just mean that in the sense of, physical separation. I think COVID kind of made that a lot more prominent these days, but also we have this, diversity in mental aspects as well. We also have issues with hardware utilization. We have some great toys. A lot of great toys are landing on the desks of researchers. We're talking about like new headsets. Everyone's got some very powerful mobile phones in their pockets, and no one's using them. And rarely using them to their fullest if they are using them at all. And so at the end of the day, what I think we have here is a waste of resources, and I mean that in terms of hardware, software, time, funding, all that sorts of things. And I think it raises a lot of questions about the defendability of the analysis that we're doing if we're not using or not able to use all these tools to their fullest. And so and I say we, I kind of mean like the visualization group at NREL, we think that some collaborative visualization can kind of help out with some of these aspects. We can think about these sorts of tools being able to bring more brain power onto certain problems, more computational power into certain problems, and provide crucial alternative perspectives on a problem. I mean that not just in, okay, we have multiple people, but also through different hardware, because different hardware, different tools can let you look at the data in different ways. And so we think that some of these techniques can help reduce some of the friction in team efforts and things like that. However, a lot of the current approaches to tooling, and I don't think this is just in visualization, but across the whole spectra of software, are stovepiped. They're very much siloed off. Everyone's got their own little section of tooling that just works there that they're very familiar with, and other people have their own little ecosystem kind of going on there. And a lot of these a lot of these techniques are kind of destructive to workflows, and that's definitely a non-starter. If you go up to any research, you say, hey, you can do collaborative viz, but you just have to move your entire workflow over to ParaView or whatever, and they'll be like, no, we don't use that, go away, is basically what they tell us. It's a non-starter. So, change is a cost, always a cost, and the limit to what change is acceptable to some group it can be very, very low. So, that's not unexpected. A lot of these workflows have been built up over decades, and you can't just say, hey, throw away, several 20 years of work on things like this. Some of these techniques require have heavy technology requirements and have some pretty nasty learning curves. So again, you can't just say, hey, use this new thing. You have to spend 6 weeks learning, just how to press a button. So that doesn't work either. And at the end of the day, we just have a lot of great tools, a lot of great techniques, and people just aren't using any of those. So what I'd like to do is I want to try to fix that, at least, try to improve the situation. I want, teams to be able to work together and do collaborative visualization and analysis. I want the different tools that we're working on to be able to talk to each other. I want people to be able to build web pages that can steer simulations without having to write a bunch of custom code. I want people to be able to be in an interactive immersive visualization and using their hands to move things around, and I want the simulation to react to that. I want to glue software together. So to that end, we've been working on something called NOODLES. If you want to know about the name is actually a backronym. We just made it up to kind of annoy leadership, so we can have a lot of pasta-based puns in our software. It really just is a lightweight protocol at its core, with a little bit of associated messaging semantics on top of that. Where its core support is in synchronizing 3D interactive visualizations. We have a lesser focus on the 2D visualizations and web pages. We think other people can do that maybe a little bit better, so we're not going to step on their feet. We also have this notion of being able to send some data back and forth through a concept of tables And we also have a remote procedure call API that people can use as part of this whole thing. So you're kind of taking a step back in what a NOODLES session might look like. We have, on the, let's see, get that little pointer here to work. Does that work? Yeah, perfect. All right, so we have on one side, you may have some arbitrary application, and this is truly arbitrary. It can be anything on one side. This application is going to be building some sort of 3D visualization. And then on the other side, we have a bunch of clients that would like to synchronize with this visualization. Again, these can be completely arbitrary, and they may have some libraries to help them speak this NOODLES protocol between them. And the only thing that I'm talking about here that we really want to focus on is this part right here in the middle, this NOODLES part. I don't care what your application is. I don't care what your client is. All I'm working on is this NOODLES thing to try to help them talk a common language. And of course, we're not limited to just one client. The idea is you can have a whole bunch of ones connecting to you. So an example of this kind of in practice might be something like AMR Wind. So if you don't know what AMR Wind is, it's a very, very large wind simulation toolkit built on AMREX. It's a multi-resolution, wind simulation driver. And through NOODLES, we want, clients to be able to connect. So for example, you could have one client that's a VR client, someone's got a headset on, and they're looking at isosurfaces of this simulation as it's running. You may have a web client that's looking at slices of this wind simulation as it's running. You could have an immersive client that maybe is steering the simulation with someone with their hands in the cave. Or you could have a Python client. And I kind of want to harp on this last one a little bit here too. We're talking about these other ones are graphical tools, but Python, it's very command line based. And we want to make sure that people can still use those tools too. So you can sit there, use your repo, use the tools you're familiar with, use your Jupyter notebooks if you have it, so that you don't have to abandon that and use something else. So clients, to use this protocol, you don't have to have a head. You don't have to have graphics. And here's kind of a high-level example of some of the messages that we might be getting across the wire here. So we have this notion of a scene graph and the manipulation of the scene graph. You don't have to use it if you don't want to, but you can. So we can talk about entities being created and moved. We can attach geometry to that. We have signals that might be coming from the server to clients saying, hey, something has changed, a simulation is completed, or oh no, something is crashing or on fire, things like that. We also have some table stuff in there. On the other side, we have clients being able to send to the server, hey, can you set the time of this visualization to something? Or hey, can you activate an entity? We have a notion of like clicking on objects so the server can take action based on that. We also have an optional notion of viewpoints that you can kind of keep track of where people are kind of looking in your visualization. So, going back to the context and the core problems that, I kind of mentioned at the start of this, we had some principles that we kind of distilled down into these 4 containers that kind of drove the development of this protocol. And the 4 containers are kind of rough here, but, the first one is minimally invasive. And I mean that in many different contexts. Like, we don't really want to, fiddle with people's workflows. We want there to be a very easy translation between what they're doing and NOODLES. That also means we don't want it to be horribly difficult for them to actually integrate the library into their code base. And I mean that by like linking and, adding in a whole bunch of extra dependencies, because that tends to make HPC people very unhappy when you add in like, 100 megabytes of extra libraries that they have to load in. We need to be open in interpretation. So focusing a lot on saying what we'd like to draw, but not how to draw it, making each client responsible kind of for how they want to present the data, right? It doesn't make sense for you to try to force a laptop-like viewpoint for a VR headset. It doesn't make sense at all. Another one is composition. And, we don't want this to be like some sort of foundational work that everyone has to build off of. Everyone needs to change here. We want to just kind of provide a building block that other people can build in addition with other things. And that does include other collaborative viz protocols if the occasion calls for it. We want this to be just one little thing that people can quickly add in to this larger project. Be more glue. And as we progressed, we kind of realized through a couple of iterations that we definitely have to be tech minimal. Like I said, we don't want people to bring in 100 megabytes of extra dependencies, but really keep this thing lightweight. Basically, the only hard requirement we have right now is that you have a library that can encode stuff into CBOR, which is like a binary JSON thing. That's about it. The biggest one is that this should be a protocol and must remain a protocol. Again, that's the only thing I want to talk about is just a language for these applications to speak. A lot of advantages there. As a protocol, any tool that speaks this language can participate, and I do mean any, and that means if you have a MATLAB script and it can send bytes, you can participate. If you have a VR headset and it can at least get to the internet, you can participate. It also means that we're kind of agnostic to transport. So people can use WebSockets, regular sockets, Bluetooth. You could use infrared if you wanted to. It doesn't really matter. It also means that we're kind of independent of the software stack. So, if I get hit by a bus and I can't work on this anymore, as long as you can, read the specification, you can write your own code and still interact with all the other tools that do implement noodles. And of course, if you don't like the way that I've implemented something, you can go off and write your own. So it's kind of open to that kind of thing. I also kind of want to point out what noodles is not, because you talk a lot about visualization, and I don't want to step on people's toes here. So noodles is not VTK, the visualization toolkit. We actually have no notion of specific visualization or analysis algorithms in noodles itself. It knows nothing about that. And that's by design, because those algorithms can change, and people way smarter than me can develop even better implementations of those algorithms than I can. So noodles doesn't know anything about that. We're not ParaView or Visit or Vapor or anything like that. Those are, those large scale data science exploration platforms. We're a protocol. We're glue. We're not D3 or, any of those, a new JavaScript framework. We can use those, but, you can glue those to noodles, but we don't want to be anything like that. We're also not NVIDIA Omniverse. And if you don't know what Omniverse is, it's this large NVIDIA-sponsored ecosystem of tools and plugins for collaborating on things like movies and games. And I've actually seen it done for some scientific visualization as well. But we're not that. We have these different objectives. They're this large platform. They have some hardware requirements. We're just a protocol. We're just a little bit of glue. So just in that, we're a lot like the web with HTTP. You just have arbitrary servers and browsers. They're just talking HTTP. We're the same thing with noodles. And the thing I really like about this is, by adding a client and a server to the same bit of software, you can get neat effects and start thinking of things in terms of pipes. So, you can write a wonderful little, shell script that pipes data from one application to the next and just kind of compose by just gluing that together. You can do the same thing with noodles then, where you have some data that comes in, it can do a little transformation and then spit it back out. And, here's an example of this kind of in composition. So you can imagine that we have simulations exporting isosurfaces. We have a node that just does decimation that reduces the geometry, so it's not so heavy, and you can send that off to a web client or a VR headset for consumption. The undecimated frames can be kind of merged in with a metadata server. The metadata server could be saying like, oh, here's some job information, here's your disk quota and stuff like that. Glue that together, and then you can send that off to the immersive space, or you can send that to record, so you can, get an idea of what happened and kind of get that ledger of discovery, things like that. Speaking of kind of ecosystem with that, this is kind of a noisy slide, but this kind of shows you what we're building here. Everything is a little beta, a little alpha, kind of a smaller team, but we have a lot of folks using it already. We have a lot of libraries to help glue this stuff into your applications. So Rust, C++, Python, we have some Unity stuff in there. Platforms, so we have some client-specific platforms to help people look at Noodles streams on their platforms. We've got stuff for the Magic Leap 2, the Vision Pro, our immersive space at NREL, laptop or desktop web, things like that. We have plugins to help you take your foundational Viz frameworks and pipe some of their output into Noodles, so stuff like BTK. We can do stuff with Blender. We've got working on some stuff for AMREX directly instead of using any intermediate libraries, some stuff for ParaView. Apps, these are like actual visualization-specific servers. So we have stuff for the power systems group at NREL. They can use this to explore their high-dimensional data sets. We can just export arbitrary geometry. We'll be talking about some of this stuff later. Tools, these are like arbitrary tools that you can just grab and use. We have merge streams, decimator, remote rendering for federated rendering for large-scale scenes. Recording and replaying, I think, is actually really neat because that basically just records your session to disk. So you can sort of keep a ledger of discovery as you're kind of going through your visualization session and mark say, hey, we found this feature at this time. over here, and then you can replay that later on as you were discovering it and find those features again and show people how you found them. So I'd kind of like to quickly go through some few use cases and some studies that just kind of show off how we're using Noodles at NREL right now. The first up is Exawind. If you haven't heard of it, Exawind was part of the Exascale computing project, which came to the close several months ago now. The idea for this project was to deliver the code and the infrastructure for these large field multi-turbine blade resolve simulations. And we're talking these 40 billion cell simulations that are trying to get feature sizes down to the microns near the blades and things like that. These are insanely huge. And in order to do that, the Exawind team, they did hybrid simulations. So they had AMR wind as a sort of background simulation to kind of capture the whole field flow, and then to get the near blade stuff, they used NALU wind to capture that. So, coupling these two simulations together. And in sim, that works very well, but in visualization, it does not work very well at all. This really broke kind of the workflows for traditional viz. At this scale, things like VTK started breaking down. And that's okay. That's kind of expected. That's the whole point of the project, right? It's like, hey, we have these huge sets. Where do things break? Let's fix them. So we had some breakage in VTK and things, so we couldn't use that for the AMR wind data set. But we could use some other tools. There's a combustion group that had a tool called Pele analysis that could give us the isosurfaces from that instead. So what we really needed to do was kind of glue together a bunch of different tools to get us a cohesive viz of what was happening there. And so we could use Noodles to kind of do that. We used, we had Pele analysis looking at the AMR wind data set. We could use ParaView as standard. That didn't break on the NALU wind data set. And we could all just pipe that into Noodles through a tool called Platter. And here we have a couple of shots of, here you can see it on the bottom there. We have the kind of isosurface of one of these shots kind of in the cave. And we also have the Vision Pro. And I actually have a little video of that here. So here's a researcher wearing the Vision Pro with the data set right in his room. Kind of a lower quality visual, video. So thank you, PowerPoint, for that. But and also the researcher asks that you ignore all the junk in his house. But you can sort of see you can get all this data right in your house. It's kind of nice. So quickly moving on. Next is command and control. This is kind of like more of an esoteric kind of a use case, but still pretty neat. So at our visualization lab, we have a high resolution display wall. It's 100 megapixels. So it's basically just 12 4K monitors we just kind of squished together. And these walls, they're really neat. They get you that kind of macro and micro view of your data at the same time. And by that, I mean, like, you can put a huge plot of data up there and take your step back, and you can start to see patterns kind of emerge from a low frequency kind of view of the data. And when you want to get that high frequency view, that high fidelity view, you just take a step forward, and then you can sort of make out, individual plot lines or individual cells or whatever you're plotting. Now, the problem is that, trying to use these displays with traditional software is a real pain. We have our keyboard and mouse. And let me tell you that trying to use a keyboard and mouse on essentially a 16K monitor, is impossible. Every little button is about this size, and you're standing at a podium that's farther away, and you're just squinting there trying to click on things. It just does not work well. And I know that you can do like UI scaling for these things, but we also found out that a lot of software that people want to use doesn't respond well to the UI scaling. So they'd have like these fuzzy, low resolution buffers that are using the wrong size, and it just does not work. We have to use one-to-one. So we have this problem, and I should also say that, just using keyboard shortcuts with this does not work very well at all, because you have to kind of hold this keyboard while you're standing in front of a monitor, and it's just all awkward. So we quickly coded up a tool that just watches the X server and just pulls images off of the active windows and just kind of displays it in a little geometry. You just kind of load this stream up in a web client, and you just got to tap on a window, and it just brings a window front and center, maximizes it, and gets it all ready for you. Very handy. Just that alone has been very useful for a lot of folks. You just hand them an iPad and say, here you go. So it's quite nice. We're not 100% done with it. We want to be able to launch specific applications or load specific data sets and things like that. But just that small amount has already been able to really help folks Next up is some AI stuff. Yeah, we're on the hype train of that as well. One of the longer term things that we've wanted to do for a long time is to kind of bring AI as an active participant in analysis. And by that, I mean, having a machine kind of looking at the same thing everyone else is looking at and kind of guiding you along. We think it can help do things like reduce the bias in your analysis, because it could be watching the scene and saying, hey, you spend a long time looking at this part of the viz. You didn't spend any time looking at that part of the viz, and that's got some interesting stuff too. You sure you want to take, why don't you take a look over there? Helping you kind of reduce what you think is reduce what the researcher thinks is interesting and just kind of make it all flat. It also can help in working with the specific tools. It takes some expertise to assemble a visualization pipeline that can get you your data to something actionable. And we think AI can sort of smooth that out there by helping you build those workflows. And for me, one of the best parts I think that AI can help is improve how you actually use your devices. I don't know if you've ever used those headsets, but have you ever tried to type on one of these headsets? They're terrible. You have to sometimes point a little laser pointer at a keyboard and you have to type by pressing a button, or you have to put your hands out and you have to try to touch a keyboard that disappears when your hands go through it every so often. It's horrible. So we think that AI can kind of help you out a little bit there. This is definitely a work in progress, but we already have a simple solution that we can start playing around with. NOODLES exports our PC. So we have a listing from a server of all the calls you can make on that server that includes documentation and argument expectations. So what we do is we take that whole listing and we just sort of stick it after some formatting in front of a prompt that we send off to a large language model like ChatGPT. And then with you have your user type a request, and the model will say, okay, based on what the user is giving me, what call or calls should I make and what arguments should I pass along to that server? And it just kind of sends it along from there. It's a little rough right now. Right now we're using ChatGPT, and every so often it seems to think that we're like a Minecraft server or something and sends a weird request. So we've got some issues with that. Maybe I should have changed the API to be more like a game or something. I don't know. But here's an example of some of my interns right now using our prototype here. So they're just asking to invoke a function, and that will pull off a combustion data set. Right now it's all text, but we could probably do some speech too. And he's just going to move around a little bit. And oh, there's a combustion data set with a specific color. So again, a little rough, but we already can do stuff like, hey, go forward, go backwards. So that just smooths things out very nicely. We're going to try to extend it this week to get it to do stuff like, hey, give me an isosurface at this value, and have it generate that on the fly and send it up. We also think we can do some object recognition as well. And say stuff like, hey, move that turbine over there, and it'll go figure out what's the turbine and help you move it. So we just need a little more consistency in the LLM. Maybe we should just be running our own. I don't know. So I just want to get to the future work. We have a lot we've done, but we have a lot to go. We have a lot more client apps we'd like to make it easier. We have stuff like phones that we'd like to work on. It's all just a question of time and getting more people to write code. We want to improve our libraries, add more functionality into the specification. One thing we'd like to do is, one thing we do in our cave very frequently is like real-time particle advection, and it's really hard to kind of communicate that kind of idea across NOODLES at the moment. So we think we need to do stuff like shipping some code like a WASM or WebAssembly block to a client that they can optionally use to help get some more functionality and execute that in a sandbox or something. We're thinking of some more tools, digital twin modeling. One open question is, how do you connect all these pipes? Like I showed a little, setup where you can have a simulation decimating your data and sending it off to other things. And that's easy to do when you're working on a command line. You're just piping things together. But when you're working with things that do network connections, how do you create that sort of topology? Kind of an open question, but we think some clever container work here might help solve that problem. And of course, we got plenty more on the AI front. So a little fast, but I wanted to get you guys to lunch. So thank you very much.
Yeah, thank you, Nicholas. Do we have any questions in the room? one question here.
This is more of a curiosity question and might be way too long to answer, but how do you validate that your like visualizations are correct or like Noodles is working as expected?
Right. So, we make sure that, we can validate against the traditional frameworks that do work. So you can take something like VTK and make sure what you're seeing in ParaView, which uses VTK, is matching what you're going to get through there. And of course, you can dump the geometry from both, and you can do a triangle by triangle comparison to make sure everything is exactly what you want.
Thanks.
Yeah, thanks for the talk. I think you alluded to this in that future work slide, but so like for the Exowind example, there was that platter step that was, sort of combining the outputs from the two different models. Where does that happen on the modeling computers? Does it happen on the client computer? Is it totally agnostic?
It's totally agnostic. For our work, we put that on a fairly fat machine because those meshes were pretty huge. But yeah, you could put that anywhere if you wanted to. You could even put that in the cloud to make it easier to run.
Okay, so basically whoever's coming up with that pipeline sort of determines where that's going to happen.
Exactly, yeah.
Any more questions? Let's thank Nicholas one more time. And that concludes this morning's session. So thank you again to all of our speakers this morning. Now we're going to take a break for lunch and we'll be back at 1 o'clock. Thank you.
No cookies.
Like that, okay, and then.
Hello, everybody. We're gonna start like in 4 minutes. All right, so I think we're gonna start the afternoon session here. My name is Maggie, and I'm going to welcome you back to the afternoon session today. We have our first speaker with us here, John Hardy Gotway. He's gonna present his talk titled Documenting Best Practices Across the Research Applications Lab and Beyond Using GitHub and Read the Docs. Welcome.
Thank you very much. Good afternoon, everyone. My name is John Halley Gotway. I've been working in as a software engineer in the Research Applications Lab for about 20 years. I'll apologize up front. I mean, this is a very NCAR, UCAR specific talk, but hopefully the GitHub details I'm going to talk about will apply more broadly. So I'm going to talk about a grassroots effort that a few of us have been pursuing over the last year or so. On the face of it, it's technically a documentation workflow, but stepping back a bit, it's more asking larger questions about how we communicate with each other and share ideas with the goal of making the things we do more efficient and effective. So, let's see. There we go. So I'll start by jumping right to the final result before working my way backward. So the website shown here is accessible at the URL listed at the bottom. However, it's password protected. You must authenticate with your CIT credentials to see it. The content is meant to be internal to the organization rather than publicly available. And while it's currently labeled with Research Applications Lab, I hope this type of content could be defined more broadly across NCAR and UCAR. So this is really a proof of concept that we've been working on for the last year or so. And basically see if it gets traction, see if it has legs, and see if we can make progress in this area. The goal is to document peer-to-peer, employee-to-employee advice about what works well on your projects and teams. So if you expand the left-hand navigation, you'll see that there's two top-level sections. The first one that we've titled Best Practice Advice. It contains a list of topics that are what I would say are ripe for the sharing of ideas. The list is not exhaustive. It's just the topics we initially included just for ideas. So if you actually click through them, I think you'll be pretty disappointed actually. While the list of topics is long, the actual examples are very short. There's only 4 of them so far. So what I'm really going to be talking about here is the workflow and the idea, and hopefully get some feedback from you all. The other top level item is titled How to Contribute. So it contains step-by-step instructions for the workflow to add new material to the advice section and edit existing content. You'll see that the steps here include checking repository access, writing up an issue to describe your work, working on a feature branch or a fork, and finally submitting, reviewing, and merging a pull request. So who is working on this? Actually, these are the questions I hope to address in my talk, starting with who's working on it, why am I talking about best practices, what are those, where should this content live, what has been done so far, how is it going, and what should we do in the future. So first of all, Julie Prostopnik is an engineer in RAL that I've been working with for several years on the MET Plus verification, or MET Plus project, which is software for verified numerical weather prediction model output against observations and analyses. And she's our documentation lead, so she knows a lot about read the docs. Curtis Walker is a project scientist, also in RAL. I participate with him on the RAL Communications Committee, where we discuss topics like this, how to communicate best practices and share ideas with each other. And so moving on to the next question, why am I talking about best practices? I wouldn't have been talking about it 10 years ago, but I searched through my email and found that it was 10 years ago that we switched to Gmail. And in the years since, we've adopted all sorts of Google products. So there's Google Calendar, Drive, Docs, Chat, Google Spaces, and even the slides that I'm presenting now are Google Slides. So every software update from Google brings new fixes and features, whether we're aware of them or not. And I would say that really thinking about over the last 10 years, the Google product suite has really revolutionized the way we work together and the way we collaborate. So then in 2019 with COVID, shifting to remote work, there was an explosion of communication tools. And personally, I've used Google Meet, Zoom, Teams, WebEx, Skype, GoToMeeting, all these platforms at various points. And then along the way, there's all these other tools that have grown in popularity. Containerization through Docker, GitHub for version control. I use Slack every day for team communication, read the docs for documentation, Trello, some folks use Trello for project management. So I think these tools really have fundamentally changed the way I do my job personally. And these are just the ones that I use. I'm sure everybody has their own logos they could throw up on this slide with all these other tools that are useful to them for their particular projects or teams. So personally, I'm looking for advice about what works well across the organization, what tools in particular are effective for what purposes. And I think that this is something that should be crowdsourced from staff rather than defined in a top-down way. We get a lot of latitude at UCAR about how we do our jobs. And so this is an attempt to give us an opportunity to tell each other about that. So what are best practices? I would say it's actually surprisingly difficult to define, or at least it's difficult to agree on a common definition. In RAL, we're also beginning the transition to Sundog for our internal lab information, and that will eventually replace the static for-staff portion of our website. I'm kind of astounded that we've gone this long without a great intranet, and I'm excited how consolidating on Sundog will help us get and stay organized. But deciding what it should be defined as a procedure or policy is different from a best practice, and that's where those details can get pretty murky. So for example, project management could be done effectively, let's say using 5 different platforms, 5 different tool sets. And there's pros and cons to each. And it would be good to have a place to write down what those pros and cons are, so that when you are starting a new project, you don't start from scratch. You can leverage the experiences of your colleagues when deciding how to proceed. But that's different from how to fill out a travel authorization form. You know, there's a way of doing that, and that should be documented on our website, our internal website, on Sundog, something like that. There's no question about it. There's no room for opinion. And I would argue actually that there will never be a best solution for project management. There's going to be choices, and some are going to be better or worse. And really, the term best practice is not a very good name at all. It's presumptuous. There's seldom a best of anything, but I've used it because it implies the right idea, you know, even with its shortcomings. Some alternate definitions or some alternate names in use out there are community practice or promising practice or leading practice. One that I just made up is proud practice, because I think it emphasizes the right thing. This is something that you're proud of, that works well, and that you want to share with other people. So now that I've hopefully established the need or the reason for pursuing this, where should it live? So Julie and Curtis and I discussed these options. So the first obvious one was the RAL for staff page. It has the right access permissions. It's limited with you know, you have to log on with your CIT credentials to see it. But the problem is it's too top down and static. It really limits staff contributions. It's not a good platform for crowdsourcing information. Sundog was an obvious other choice. When we started this a year ago, and our lab hadn't transitioned over to it yet, we had more questions than answers. It felt too early, but there is good controlled access and good potential for collaboration. Google Docs and Google Drive are widely known, highly collaborative, very well used, but there's little built-in organization or workflow. It's kind of a junk drawer of information sometimes, unless you put a lot of effort into keeping it well organized. UCAR Wiki is also well known and collaborative. It provides a bit more structure than Google, but it's less widely used than Google Drive, and there's no built-in workflow either, or at least none that I'm aware of. And so perhaps predictably, a couple of engineers will land on GitHub and read the docs as a great workflow for proving new content with great organization and a really good-looking HTML result, but the complexity is intimidating, I would say, is a shortcoming. So what have we done so far? Let me dive into some details. About a year ago, I created this repository in the NCAR GitHub organization named RAL Best Practices. It's a very simple repository. It really just contains a README file, a doc subdirectory where the actual documentation content lives, and a .github directory, which contains issue and pull request templates, along with a GitHub action workflow. And thanks to Simon for his talk earlier this morning, laying a lot out all the benefits of GitHub. I'm fully on board with that, and I spent most of the lunch talking to him about how they're organized on GitHub. So while this repo is private, all members of the RAL GitHub team have write access. And then prior to this talk, I also added all 469 members of the UCAR GitHub team with read access. So really, we do want our colleagues to create issues and do work and submit pull requests and update the material that lives there. So let me talk a little bit about the GitHub features we're leveraging. And again, I'll really, these aren't new ideas. This is just leveraging all of our experience, especially over the last 3 or 4 years for the Met Plus project in RAL, where we migrated over to all things GitHub. And so we're taking the most effective features from that and applying it to this other issue that we think needs to be addressed. So we turned on GitHub discussions, that feature, to facilitate conversations about these best practices. So the discussion content can live right there in the same place as the actual best practice advice itself. And they can be organized into different categories like announcements, Q&A, or asking for help. We created these issue templates that live in the .github repository for adding new advice or updating an existing one. So when you go create a new issue, it serves up an option to say, are you adding a new thing or are you updating one? And based on which which option you choose, it'll serve up a different template, making sure to ask, remind you what material you should add to the issue. Similarly, there's a pull request template. So every time a pull request is submitted, you're served up with this template to ask the right question and get questions and give you a checklist of the things you should do to kind of remind you of the process. We define 28 different labels to help keep our issues organized. We have blue ones for categories, so basically the topic area. Purple ones are the organization labels, so you can keep track of where the ideas are coming from, which lab or which program or project. We use multicolored priority labels to assign some relative priority, although that's pretty subjective. And then the brown type labels differentiate between new content and updating existing content. So we learned through the Met Plus project that keeping issues organized as you create them really helps. And lastly, I want to point out that we have a branch protection rule. So we just have a main branch here and have folks work on feature branches or forks. But in order to merge your pull request, you have to have it approved by at least one person with right access to the repository. So at a minimum, someone proposes a new content where they say, hey, this is a great way of doing something like project management or employee appreciation or anything else. And they write it up and they have at least one other person review what they're writing and approve it. And the great thing about it is all very traceable. You know who committed who proposed the content, who approved the content. And so since this is all internal, we can police ourselves and keep track of who's adding what. And if there's any questions or discussion to be had, you can do it right there in the GitHub discussion board. So next, I'll talk a little bit about how we're using GitHub Actions. And this is one of my favorite things one of my favorite features of GitHub that's evolved over the last few years. So on the Met Plus project I mentioned, we automate at least 7 different tasks like building the code, building documentation, automated running of tests, regression tests, scanning the code with SonarQube, which is a static code analysis tool that the Air Force funds us to use. And there's a few other things. And each action is defined by a YAML file that contains a workflow. And in this repository, we're just using a single workflow. It's for building the documentation. And the rules here define when this workflow is run. So you see it's on pushes to the main or feature branches and on any pull request. So, and then additionally, the workflow dispatch option enables you to manually trigger it from the GitHub website. And this build documentation workflow is pretty simple. It's a single job. It runs multiple steps. The steps basically check out the code, build a Python environment, install any needed dependencies, and run make HTML to build the documentation using this Sphinx workflow. At the end, it saves off the result. The HTML result is an artifact, which is a zip file containing the rendered HTML files. So there's the documentation artifact that gets created. And we do 2 things with this. The first thing is when someone submits a pull request and this workflow is triggered, the docs are automatically built and saved as an artifact. The instructions for the reviewer say, go download that artifact, open up HTML the index file, and review the proposed changes, the HTML, the proposed changes right there on your laptop. So you can make sure that they render well and comment on the content. The second thing we do is on our web server in RAL, I run this pull GHA artifact script that's run through cron hourly, and it uses this GitHub command line interface to pull and publish the most recent main branch artifact. And it serves up the result there at the URL listed on the bottom. So those of you who are familiar with running Read the Docs might say, what are you doing? You're crazy. You should just be using Read the Docs to publish this, and I totally agree. In fact, for Met Plus, we have documentation that's built and served up through Read the Docs for 8 different repositories. Those repositories are all public, so all of this is free and automated and easy. And like I mentioned, it uses the documentation is formatted in restructured text, a lightweight markup language, and it rendered through the Sphinx Python package.
Read the Docs is free for open source and public repositories for the community edition. The business edition costs between $50 and $250 a month. And at the highest level, or at the lowest level, I think you can authenticate using your GitHub credentials. At the $250 a month level, you can authenticate using your Google sign-on like we use for so much else here at NCAR. But since this is a grassroots effort, we basically had no budget. We chose to go with the GitHub Action workaround rather than actually paying for Read the Docs for Business. But long-term, I sure would like NCAR or perhaps just my lab to purchase it so we can use Read the Docs for our internal documentation. So I've mentioned a lot about the workflow and the content. I haven't provided any good examples yet. So in reality, like I said, across all these categories, we only have 4 actual examples. And I'll talk about one that I added that I find really useful. And that is adding I'm in the Joint Numerical Testbed program. I created a program calendar. And this is some content that lives in the best practice guide about it. And each one starts with a table of metadata. So what is the title of this? What is the topic being addressed? When did we add it? What's the time period if applicable? What project or program it applies to the JNT program? I'm the contact, and so is Mike Eck, who's the program director, and Catherine Newman, who is the science deputy. And what are keywords for this? This is about communication tools in the JNT. And so then there's a description of the best practice, and it basically just describes how we use a shared Google Calendar to communicate 4 types of things across our program. The first one is general meetings of interest. The second thing is we have events to indicate who will be visiting when, who they're meeting with, that sort of thing. Third thing is when Mike Eck is out of town, who's going to be serving as the acting director, so that staff know, hey, Mike's gone. Do I need to talk to John? Do I need to talk to Catherine? Just communicating that in one place. And then finally, the thing that I really like about it is that I've set up a Google script to run hourly and look at every user that's in the RAL JNT Google group and go look at their calendars and automatically import any events that say PTO or out of office. So basically this serves as an automated way of generating a vacation calendar, an out of office calendar for our program. So if you want to know who's around when, there's one spot where you can go look and find out that information. And the great thing about it is I've actually, on the page there, if you click the RAL JNT out of office Google script, all the content's right there. So all the details you need to replicate this live on the best practice page, and you can go grab it and use it for yourself. So I imagine there's a lot of conversations that happen in the hallway. Say, oh, we're using Trello for our project management. We find it really useful. Someone else will say, oh, that's great. But what you really need are the details. And this is meant as a mechanism to serve up the amount of details that are needed to replicate the thing that's working well for your project. All right, so how is this going? Honestly, it's not great. We did a RAL Lunch and Learn on this topic last December, and there's a GitHub discussion that's linked there. So if you want to see details about that, you can go to the GitHub discussion page and even watch the hour-long video of our RAL Lunch and Learn. There was some interest in it, but there's very little follow-through. I'll note that the contribution instructions are very detailed, and where possible, we included instructions for doing all this through the GitHub website to make it more accessible or via the command line. But I do think the bar for contributing is still too high. But more importantly, we're all probably too busy to find time to reflect on what's working well and share details about that. As soon as you've accomplished something, you're on to the next challenge for your project. And it's hard to take time to step back and think about what can I share with my colleagues. It's something we're not in the habit of doing. So what should we do? I think we've pushed this about as far as we can for the time being without having any actual funding to support it. We're going to submit a proposal to the RAL Opportunity Fund in August to try to make more progress, but there's so many cool scientific developments against which this is competing. It's probably not held it probably doesn't have the priority that it needs to make progress. So big picture, we think it'd be wise to meet with the individual RAL programs to identify potential topics. So have some funding to talk to the program directors and brainstorm what's working well in their program and share it with others. I'd like to see a closer connection with the RAL Lunch and Learn meetings. So when those presentations address best practices, which they often do, I'd obviously like a corresponding edition here so we can document it instead of having it live in some far, some Google Drive somewhere that we can never remember where to find that information. Similarly, I'd like to work closer with the NCAR and UCAR affinity groups that should be diving into these sorts of questions anyway. And I think there's an opportunity to emphasize to staff that documenting a best practice could serve as a really nice SMART goal. And to make the submissions easier, I think we should add a Google Form submission option to really lower the bar so that people that work at UCAR that don't have a GitHub login and have no interest in gaining one could still provide content, but through a Google form, and then have it be someone's job to translate that into the documentation. I do think we could consider making the scope broader than RAL. I'm curious to see what interest, if any, there is beyond RAL. I definitely think we should purchase Read the Docs for Business. And like I mentioned, I'd like to see it NCAR wide, but we'll see. And finally, maybe we should scrap all of this and switch to using Sundog instead. Julie and Curtis and I discussed this, and we worked on this based on our experience and based on the workflow we know works well for code, obviously. But the most important thing is the sharing of the ideas. And if that's done efficiently and effectively through Sundog, then that's great too. So we're not totally tied to this solution, but just propose it as a good one to consider. And with that, I'll leave you with my email address and Julie and Curtis's as well, and take any questions you may have.
Thank you very much, Jen. Thank you. Any questions? Oh, there's one over there.
So the goal that you have for this is obviously laudable. I don't think anybody would disagree that we want to have an organization that learns. I wanted to point out that you basically have selected or pre-selected one strategy for how to create a learning organization, and I would call it the crowdsourcing strategy. You basically are building a crowdsourcing system. Everything you mentioned is a detail in how you do that, but it's all within that kind of, or under that umbrella of crowdsourcing. And I wanted to suggest that you could also look at other umbrellas or other possible ways to do this. And you might even want to have a best practice for best practices. In other words, look at other ways that other organizations have had to create learning organizations. And to motivate that a little bit, I wanted to share some of the pitfalls that I've observed in the crowdsourcing method for doing this, and ask if you have come up with solutions to any of these. One of them, I have three, is overlapping best practices. That is to say, when you allow people to add their own best practice, inevitably they're going to start to overlap. Different people will put in different things thinking they're distinct when really they're about the same topic. And somebody has to be responsible then for resolving those overlaps. And even more insidiously, sometimes the overlaps make sense in that there's like a big thing, and then there are little, sub parts of that. And the question then becomes, do you want to have different best practice entries for the little things, or, glom them all into the big thing? So, number two is, let me see if I can read my writing here. Duplication of content. Wait a minute, that's the same. Oh yeah, right. Duplication of content not in your system, but with other systems. So I imagine around NCAR there are all kinds of resources where people have been collecting knowledge about things. And there may actually already be a best practice guide in somebody else's system. And the question then becomes, what do you do when you want to include that in your system? Do you ask them to duplicate it in your system? Do you ask them to refer to the existing thing? What if the existing thing has some of the information that's important, but not all of it? Do you refer and then add, append or whatever? So when there's duplication with other people's systems, that can be a challenge. And then the last one is maintenance. This is the one that kills these systems, is how do you keep all this stuff up to date? Even if you could put in all the content for each of the best practices, it almost instantly becomes obsolete. And it becomes then a maintenance task. And what I've seen happen in other systems is that there are lots of incentives and gratifications for creating a new best practice, and there are very few for keeping it up to date over time. So I'm curious to know if you have any thoughts on any of those.
Yeah, those are all excellent points you raised. As a software engineer, I'm always looking for comprehensive, elegant solutions that address the edge cases. But I approach this totally different. This is basically a best level of effort. This is not intended to be comprehensive. Basically, what I see happen at NCAR is that we're given all this latitude to do things the way we want to do them. And all this, and when I've worked in the corporate world before, there wasn't that latitude. This was, at this organization, this is how we do it. So at NCAR, what I see is all these great ideas, all these great ways of doing things that totally overlap, right? There's so many different ways of solving the same problem. And so this is an opportunity, the intention here is saying, if we're not going to force people to do things the same way, which I don't think we should, let's give them an opportunity to write down how they are doing it in ways that do work. And make sure you fill out the metadata so that anytime anybody goes and looks at it, they know how old the content is. So yeah, if 5 years have gone by and it hasn't been updated, you should trust it less. So I do think maintenance is an important issue as well. But yeah, this is not, again, not intended to be comprehensive, not intended to be a perfect solution. It's basically a straw man to say, let's start writing down what works. Any other questions? Thanks.
Thank you very much, Jen, again. Thank you. All right. Okay, we'll start with our second talk this time. Please join me in welcoming Boaz Nash, and he will present his talk, The Sirepo Interface to Particle Accelerator Software and Potential Applications to Atmospheric Science Codes. Welcome.
Thank you. All right, good to be here. So yeah, I work at Radiosoft, which is very close to here. It's also in Boulder. And I'm going to talk about software that we developed called Sirepo, and also a bit about my experience in particle accelerators and how I feel like there's some applications in atmospheric science. And I've also just been moving in that direction in my career and learning more about it. So, okay. So I'm going to tell you a little bit about Radiosoft, and then about the particle accelerator modeling and codes. And then I'll tell you what Sirepo is and how we create user interfaces for the particle accelerator codes. And then I'm going to try to make a little bit of a scientific connection between what the problems we solve in particle accelerators and the problems solved in atmospheric science, climate science. And then one of our more recent interfaces is for the Flash code. Right? So, all right, that's what I'm going to talk about here. So, okay, so Radiosoft, let's see. Yeah, we don't have a pointer, I guess. So the Radiosoft, we have 7 full-time software developers, and we have 11 full computational scientists. And it's in a variety of disciplines. Most of them are, most of us come from particle accelerators, and I've worked I was at the European Synchrotron Radiation Facility before this, and we're kind of some of the people doing this somewhat obscure area of modeling and computation and theory for particle accelerators. And we have 3 administrative staff, and we contribute to more than 20 different workshops and conferences annually. And we're also involved in the education in particle accelerators. So we're a small company, but we have a lot of collaborations and a fair amount of expertise. I working in several different facilities. Each time I was at a different facility, I would have to use a different code. And the code did almost exactly the same thing, but it was it was a huge learning process each time. And so that was one of the things that motivated me when I working for Radiosoft, is to have a nice interface that lowers the bar for how much you have to learn to actually use a code effectively. So I actually I was the starter of this Wikipedia article on accelerator physics codes, just trying to collect together the huge range of codes that were all doing the same thing. So, for example, a synchrotron light source, there's a lot of different modeling elements. You have to model where the electrons come from. You have to, the early part, there's a code to model that acceleration piece. Then there's the storage ring. Then you have to design the magnets. Then you create X-rays and propagate them down the beam lines. And then you have to model the interaction of the X-rays with the samples, and just it's a diagram to see what these things look like. There's the electron gun, then goes to the LINAC, to the booster, and then the storage ring, and then it's stored in the storage ring for a long time, and then you create X-rays that go and hit the sample in the experiment. And so all of these pieces require modeling, and there's a lot of codes to do this. So Sirepo has, on the left here, is all the codes that Sirepo has interfaces to. It's open source, and you can just go there and try these codes out. So, and one of the things that you can do is you can then get the configuration files, and we have a Jupyter server also, and the same codes that are sitting there in Sirepo are also, they're all in Docker containers, and they can then be run, the exact same code can be run on our Jupyter server, so you can run it with a command line or a different kind of interface. This is another kind of representation of all the codes, particle accelerators and the adjacent technology, Elegant, Opal, Maddox, Scooby, Warp. There's many more, but so we've kind of consolidated them and created ways of interacting between them, and just kind of simplified the process of using all these codes. And then there's magnet design, free electron lasers, and then we've developing the technology for easily using these codes. We've kind of been expanding. So we have the flash that I'm going to talk about a little bit, which is the plasma or magnetohydrodynamics, and a laser code that we wrote, and then a few others. So we're kind of expanding beyond the particle accelerator. So that's sort of why I find myself here, is can we do something? Is there something valuable to be done with the atmospheric science codes? And then we also are involved in education. We're the main code used at the US Particle Accelerator School, and we also typically teach classes at the US Particle Accelerator School. We also have some involvement with Korea University and Stanford and University of Strathclyde. So this is an example of what one of the interfaces looks like. You see the URLs down there. You can see you go to sirepo.com. That's where you can access this. It's all in GitHub, so you can see the source there in Radiosoft Sirepo. So this is an example of an X-ray beamline. So we have all of the elements, the lenses, and the apertures, and the crystals, and the mirrors, and it's a kind of drag and drop system to create your beamline, and then you have a source of a electron source that's creating radiation, and then that passes through the beamline, and there's a lot of computational issues. There's it's Fourier optics, and there's a lot of details to get the propagation correct and know that you're getting the right result out of it. So it's another one of these expert codes that what's hard, it's often hard to even get something set up. So often the workflow is that you set something up in this interface, and then you'll download the files, the Python source, and any extra files you need, and then you can run it on the Jupyter server. This is the kind of overview of the job architecture for Sirepo. So the GUI is where you tell it to do something, you ask it to run a computation over there on the left, and then that will pass via Flask to Tornado, and then Tornado's this job supervisor that will then ask for the resources to do the job. So here's two kind of different examples. One is we have computing nodes at Radiosoft, or we also are submitting it to NERSC in Berkeley. And so either way, it doesn't look very different from the front end, but you can add additional resources, and it doesn't change the workflow too much. So they're all in Docker containers on the Radiosoft nodes, and then they use SBatch and NERSC. So you need a slightly different driver to send the computing message there. So those are kind of the full codes that we have. I wanted to talk a little bit about the connections between particle accelerators and atmospheric science. They're both kind of early areas where chaotic dynamics were really important. And so, you can predict the weather for a certain amount of time, but you can't easily run the same model for a longer time. You have to do something slightly different to predict the climate. And we have kind of similar types of issues with particle accelerators. These circular accelerators that you need to run billions of times around, and how do you know that this long-term behavior of the particle accelerator is actually correct? So one approach is to kind of create simplified models, a reduced model, and use that both just analytically and easier to think about, and also faster computationally, and it can just give you a different way to think about kind of long-term behavior of your system. So you want to be able to derive that reduced model from a real model. You don't want to just make it up out of your head. But so as an example, in particle accelerators, the simplest thing you can do is a linear model. So this is our model for the Los Alamos proton storage ring, and you can just create a linear model, for example, where the propagation of the electrons is represented by a matrix, and it allows you to easily extract kind of linear quantities. And then so you can misalign things, you can create a very realistic model, and then extract these kind of reduced quantities from it. And then nonlinear dynamics is extremely important, and we have some frameworks for dealing with that with Hamiltonians and such, and being very careful with simplexity. And then you can, in the code, you can extract these nonlinear parameters and give you a kind of reduced model representing the machine. And I'm not going to go too much. We do a lot with machine learning. I'm not going to emphasize that too much, but in a way, the neural networks are also kind of a nonlinear model. You can kind of replace, as people are talking about, you can replace your code with a neural network. So this is the example of this long-time behavior of the proton collider. It's actually the number, you want it to last for an hour. You need 1 hour of particles moving around your proton ring, like the Large Hadron Collider. And that's actually more times than the Earth has gone around, than the Earth and Sun. So it's a very long behavior for a chaotic system. And so you have to be very careful about how you set up the integration. We use symplectic integrators, and then you study the long-term behavior. And then you can kind of find these simplified models to study their properties. And so I've just kind of started learning about the analogous thing going on in atmospheric science or climate science, where so here's the simplest. So you have this Lorenz system, which is not a good model, but it's just a simplified model, but you can use it to understand some property of your climate system and the chaotic dynamics and such. So it's kind of a similar thing. It's kind of try to derive from the real model some kind of reduced model to understand these tipping points in various aspects of the climate. There's a few references I've been finding and looking up. Okay, so let me get back to Sirepo, what we've done. This is one of the more recent interfaces we've built for this Flash code, which is developed at the University of Rochester. We have a webinar on our YouTube channel by Nathan Cook, who goes through the details of how to work with this code. So it's it's a big Fortran code, very complicated, lots of ways you can put the pieces together, very much an expert system here. But you can put it together in many different ways. So there's a lot of Fortran files. We have an interface that kind of lets you choose the Fortran files you need. It builds it, and then it creates an interface based on that. So it will kind of read the files and figure out what are the relevant parameters you need, and then it will build a GUI based on what quantities, what physics is in there, and then it creates visualizations based on those. So this is going to be different. So if you go in there and look at the different examples, the set of visualizations, the set of parameters are going to be dynamically created. So that's one of our more recent applications, user interfaces. Another important aspect is that you need to combine the codes together. So we've created some software called Omega, which allows you to do a start-to-end simulation with a variety of codes. So whatever simulations exist independently, now you can just stack them on top of each other. There's code for translating the output data from one to the input data of the next, and then this is for the fast accelerator at Fermilab and the Tessa undulator, and you need 3 different codes to kind of pass through all this data. And I didn't really emphasize this, but the nice thing about these simulations is that there's just a URL associated with them. So you share the URL and you click on it, and you just immediately share your simulation with somebody. So That's some of the material. There's a lot of codes in particle accelerators that require a huge amount of expertise. And Sirepo is a convenient web-based interface that makes it easier to use and allows interoperability of the codes. It's also designed to provide an abstract way to talk about the computing resources to simplify the running on a wide range of architectures. It allows you to simplify the constructing of the reduced models, either with these linear and nonlinear models or with machine learning based models. So you can have the full model and then extract a reduced model directly from that. And then we've also created more model interfaces with increased flexibility that makes it that simplifies the build process, as we demonstrate with the Sirepo Flash. And then also a lot of simulations can be combined together. So this is sort of where we're at, and we're just we've been expanding beyond particle accelerators, and now we're interested in discussing with people and understanding better how the needs of the atmospheric science codes and see whether we could apply some of these tools there. Thank you.
Thank you very much. Any questions? And I don't see any questions on Slido either. All right, well, thank you very much. All right, so we're a little bit ahead of time, which is always good. So we are going to go to our third talk after lunch and the last one before break. Please join me in welcoming Ed Hartnett and his presentation with the title Using Doxygen to Document Fortran Sea Science Codes at the Environmental and Modeling Center, EMC. Welcome.
Thank you. Hello, everyone. Hope we're all having a good conference. Great to see so much interest in improving scientific software. I'm presenting some work today on documentation and Doxygen. It's a kind of basic skill that is, I think, too often neglected in the science world and to our cost. I've done a bunch of work here at the NOAA EMC on documentation with these collaborators that you see here. And together we have greatly improved the EMC's documentation situation. So first, let's start with a survey. How many people in the room feel that their program documentation is really excellent right now? But nobody? Okay, a couple of people. Okay, we have some room to grow then. Good documentation lowers your development costs. That's the point. I sometimes feel that there's a false dichotomy between doing it right and doing it cheap, and that's a false dichotomy because when you do it wrong, you are adding costs. And those costs might not be today, they might be next month, but when you do it right, you lower your development costs, and that means you spend less time doing software and more time doing science. That should resonate with every scientist in the room. I tried to think of a famous bad documentation mistake, and of course I remembered this, the Mars Climate Orbiter, which crashed into the back of Mars because one group of engineers was using metric and the other was using non-metric units. And I was actually working at NASA in Washington at the time that this happened, and I recall that we were subjected to much humiliation on TV with late night hosts, columnists in newspapers, all making fun of NASA for this dumb $125 million mistake that, it didn't just cause the whole loss of a mission at $125 million. That mission represented 30 years of work from the scientists on it. And because several teams of engineers did not document their work correctly, it crashed into the back of Mars instead of orbiting it. So here's a list of the software at the EMC at NOAA. We have a bunch of libraries we call collectively NCEP libs. We have a UFS utils, which is a bunch of utilities. We are responsible for the FV3 ATM component of the UFS, which does the I/O and other things, and also the UPP post-processor, which takes the output from the UFS and post-processes it in many ways for many of the downstream users that need specialized products. When we started, we had legacy documentation, which looked kind of like this at the top of our Fortran codes. I think what is so amazing about this is that if you look up in the upper right, you'll see that this was written in 2016. Fortran 77 introduced lowercase letters. So why are we still documenting like literally 45 years ago? I don't know. So we wanted to address this situation, and we selected Doxygen, which is a widely used standard documentation system. It's kind of was written in response to JavaDoc. It's the JavaDoc for C and Fortran and C++. It's very popular. A lot of projects use it. There's a lot of information online, and it produces nice HTML documentation, which I'll show you. So here's an example of some code that has Doxygen documentation. You can see we use a special comment marker instead of just the exclamation point. It's exclamation point greater than, and that lets Doxygen know this is a Doxygen comment. And then there are these words that start with the ampersand, which are special Doxygen tags. I'll go into a little bit more. What I want to mention here about this, though, is that if you look at this, it's not a large amount of extra fluff or boilerplate to document this code, right? It's actually quite terse. And here's how it comes out on the web. So Doxygen takes our programmer documentation and makes it look very pretty. It can be formatted differently. It can accept style sheets. You can put images in. It's extremely flexible. So as I've mentioned, the Doxygen documentation blocks have a special comment marker. And we need a documentation block for every file, module, module variable, defined type member, and subprogram in Fortran codes. And the reason is, if we define all of those things, then we can use Doxygen to let us know if we have anything missing. I'll explain a little bit more about that later. So there's some tags: file, date, author, param, and they do the obvious things. The param tag allows us to specify parameters, and you'll see some more examples. So here's the Doxygen documentation for a module, and you can see over here how it comes out in Doxygen. Note that along the bottom, every one of the module variables are documented with a Doxygen comment that comes after the name of the module variable. Here's another example. I think in this example, I'm trying to show that although the programmer does not have to do it, it says at the bottom, you see references and reference by. Doxygen figures out all of the functions that call this subroutine and all of the functions that it calls, and automatically links to them at the bottom. You don't have to maintain that list in your code, as was done in the legacy documentation. And here I'm showing our very first step. When we started with the legacy documentation, we just took it and plunked it into Doxygen comments, and that gave us at least a hyperlinked set of documentation that looked rather ugly, as you see, all in caps. But we've corrected all that now, and now it looks better. Okay, so when building with Doxygen, there's a file called the doxy file, which controls everything. And we build that from a doxyfile.in at configure time. So the doxy file has loads of settings, but only a few are really important for us. And I'll mention a couple of them. So how do you add, let's say you have no Doxygen at all, how do you add it to your repository? This is what we did for all of the EMC projects, and they're all done exactly the same way. We have a docs subdirectory, we add a doxyfile.in, and a landing page called userguide.md. Then we have our doxyfile processed by CMake, and the documentation build is added to make all. And this is showing the beginning of a doxy file. One of the properties you set is the project name. which you can see down there. So when we take our doxyfile.in and turn it into a doxy file, we do variable substitution. If there's anything in doxyfile.in that has ampersands around it, then it will be replaced by CMake with whatever CMake has for that value. So we see here we're able to set our input directory based on where CMake thinks our top source directory is. And other important settings are the project name, the project number, which is the version. There's a setting to optimize for Fortran, which is useful. These two settings here, references by relation and references relation, when you turn them on, that's what gives you the automatic this function calls and this function is called by at the bottom. Here's another example of some nice documentation. Okay, in CMake, at the top level, you have to enable, we have an option called Enable Docs. Again, it's the same option in all of the projects. And when it's enabled, you add the Doxygen subdirectory. And then in that Doxygen subdirectory, we have this business here, which creates the doxy file from the doxyfile.in and then adds it to the all target so that when you run make all, it builds the documentation along with it. So every documentation set has a user's guide.md, which is kind of the main landing page when you build a documentation set, and it contains kind of the top level. This code does such and such, and it contains links to the various other parts of the documentation. This is the example from UFS utils. It's in Markdown language, just like the README. You can add Markdown to Doxygen. And so this is what it looks like, the main landing page of UFS utils. Everything in blue is a hyperlink that takes you to the documentation for that thing. When you build Doxygen, you see a lot of output. It kind of starts like this, goes on, and then if there's an error, you know exactly what the problem is. When it is complete, you have an HTML directory, which contains a bunch of HTML files. One of them is index.html, and that's where the documentation starts. Okay? The rest are all different pages in there. You open index.html and you get the main landing page. And note that the version of the software is up there too. Okay, the documentation is versioned with the software, so if we have a 1.0 release, we have a 1.0 release of the documentation that goes with it. Every release gets its own documentation release. And then we use a neat feature of GitHub called GH Pages, which is has to be turned on in settings, and it's a bit odd, but what you do is you create a special branch called GH Pages. You put your built HTML on that branch, and then GitHub will display that as a separate site ending in .io, but with the same name as your project. So basically, GitHub will host your built HTML documentation for free with your project quite easily. And we do this with all of our projects. And then we put a link to that in the README. So if you go to the GitHub page and you read the README, it'll say, as it does here for complete documentation, click here, and then you get the Doxygen documentation. Okay, well, once we have all this, then we can turn on warnings, some warnings inside Doxygen, and we put that into the continuous integration system. And now, if any programmer tries to submit code without documentation, they fail continuous integration. Okay, so we're requiring documentation for all code and all code changes. Doxygen cannot check everything. It cannot check that the documentation makes sense, but it can check that it's there, and that's very important. This is a great thing to do, but you can only turn this on your project when you have fully documented everything, so you have no more warnings. Once you have that state, then you can turn this on and guarantee that no programmer introduces warnings. But getting to the state where you've eliminated all warnings is some effort. And so this shows in the CI, which is a GitHub Actions, which we've heard a lot about this conference, the output of Doxygen there. So you can see if something goes wrong, you go in there and you see what went wrong and you fix it. Okay, you know, I've been thinking recently because of some experiences I'm having at NOAA about the differences between legacy management and agile management of software. And in legacy management of software, there's frequently an attempt to try and cut stuff because everyone's always late and behind schedule. And you say, oh, well, let's just cut this phase of testing. Let's just cut working on the documentation and try and get it done. And that is a terrible mistake. And the agile approach is much better, which is to say, it has to be excellent, naturally. So if it's hard for you, then automate it more, do it more efficiently, stop complaining. And, you know, there's no excuse for documentation that's not excellent, really. Because when you have bad documentation, you are just costing your own project more time later. So you are not saving anything. Okay, so on the NCEP libs projects, we do not excuse programmers due to whatever time management problems they may be having. They must turn in documentation with their code. And all programmers on NCEP libs are responsible for the excellence of documentation. No one's allowed to say, well, that's not my part of the code, so I don't care about that. That's not how we do things. This conference talks about software engineering a lot, and it should be remembered that the point of software engineering is to lower production costs of software. So if you're still producing software like people did in the 80s, you are doing so in a very inefficient and costly and time-wasting manner, because many improvements have been made since the 80s in software development. And you need to take advantage of them, or else you're simply wasting precious science resources. And improving documentation is a great example of that, because poor documentation leads to mistakes and slower coding, and does not really save anyone any time at all. And that's my last slide. Any questions?
Thank you very much. Any questions? I also, yeah, I know we're like 30 minutes ahead or something. Yeah, literally 30 minutes. Brian?
Yeah, I'll ask a quick one.
Okay.
So, you know, you talked a lot about time and time management. For that effort to migrate the legacy docs to Doxygen, do you have a rough estimate of like the amount of time that took the project team?
Oh, that was more time than I expected. Months, really. We did it in some cases by stopping other work and just all hitting it, and then in other cases by just doing it in the background. So yeah, that was a fair amount of work. But we were starting with a lot of code.
And I guess once the legacy stuff is all converted, then what's your sense of the time investment on a continuing basis to?
Oh, it's easy peasy. Yeah, once you have it all automated, it's, you know, it's as easy as it can possibly be.
You mentioned that you had those checks to enforce documentation was being written. Have you found that the number of times, like the number of failures, has decreased over time? When you first put them in, you kind of intuitively expect that everyone would go, "Oh no, I've not written documentation," and that those checks would fail. But have you found that that has sort of tailed off over time? Have people bought into the vision that you're trying to achieve?
Yes, absolutely. Once, excuse me, once programmer becomes familiar with Doxygen, it's not a programming language. It's like a very simple markup language. So once you become a little bit familiar with it, you basically never make a mistake again. The only thing that comes up then is sometimes you misspell a parameter name or something, and you say, "Oh crap, I misspelled it." Very easy.
Oh, it must be very gratifying.
Nice. Any other questions? Oh, one more.
Obviously, you've talked about how it definitely is benefiting software developers, but have scientists been using that documentation? Do you get any sense, has it helped on their end?
Scientists are certainly using the documentation because all of these codes are used by scientist programmers at NOAA. Has it helped? I believe it has. It's hard to see because you're looking for a mistake that didn't happen. So how would you know, right?
Good point. Yeah, but cool.
But I do know that right now, when I'm asked a question about the codes from a scientist, I can point to excellent documentation that I know is 100% up to date, and I can be confident that it's correct. So that's very helpful.
Thanks.
And in particular, I will also say that one thing you have to get into as a project, like I said before, it's all about reducing costs. If you're on a project where you're answering people's questions by email or on a phone or in the meetings, you're wasting time. Instead, you answer those questions in your documentation by updating it, and you say, here's the answer, read it. If it's not complete, tell me. And then that answer serves for all future users, not just that one user. So this is how we operate projects like NetCDF, where if you call and you say, I don't understand how this works, we say, read the documentation. And if you say, that's not clear, we fix the documentation. We don't explain it to you. We fix the documentation and say, now read it again and tell if it's clear. And then the documentation improves over time. And we spend less time explaining stuff to people and more time working on programming. Okay. What else? Yes.
Another question about, so Doxygen is great for the document in the interface. Does it work? Do you use Doxygen also for user documentation, or do you see a difference between the document in the interface and user documentation? And would you use Doxygen for both or different tools?
Yeah, you can use Doxygen for user documentation as well, and it works great. Most of the software packages that I work on, the distinction is kind of blurred because the users are programmers, right? If you're using NetCDF, you're a programmer. So user documentation is also programmer documentation, but it produces very attractive documentation that you can use for any purpose.
Thanks.
So we have two more questions,
Okay.
at least. So one is from Slido here. I'm going to read it. This is from Paul. It's great to see this effort going into maintaining and modernizing venerable code. I'm also aware of your NCEP libs unit testing efforts instead of giving in to the often foolish temptation to throw it away and rewrite. Was it difficult to convince funders of the need to invest in this?
No, when I came to the EMC, it was because they wanted to do this with NCEP libs. There was a realization that the code had been neglected for too long and was causing a lot of costs. And they really wanted to get things in a more, battle-hardened state. So no, I had stakeholder support right from the beginning, and that's very, very important, because trying to do this in the face of stakeholders who don't want you to is really very difficult and impossible. So yeah, you have to convince your supervisors or your funders or your scientist boss that this is worth having and worth maintaining.
The last question is actually from me. So we do use Doxygen at Cosmic, and I don't know if that's always like that, but we have to do some initial configuration to show it on the web, on the HP. So have you had any issues? Is that easy for your audience to do? Have you had to do any training to make sure everybody is able to read the Doxygen documents?
No, because we put them up on the GH Pages branch of GitHub, and then we put a link to that in the README. So it's always there, and you click on it, and it shows you the documentation for the most recent release. And it's part of our release process to update the documentation when we do a release. So you always can see the one for the version that is the most recent version.
Okay, thank you very much. Any more questions? All right, well, thank you very much, Ed.
All right, thank you.
And what would you like to do in terms of break and then coming back? Stretch it out. All right, so we have a beautiful break here. The sun is still shining, and we're gonna stretch it out. And I see you back here at 3. Okay, thank you. Yes, dig out, huh? All right, let's see, 5 minutes. I would like to invite the members of the panel. You want them to sit over there, right?
Yes.
Presenting. Okay, sounds good. All right, so welcome back to the last session today or Wednesday, third day of the conference. And it's going to be a panel session. There will be a presentation first, and then the panel will be discussing. The title is Transforming Academic Publishing, a Jupyter Notebook-based submission ecosystem implemented for this conference for enhanced open science and reproducibility. Okay, welcome. Thank you.
All right, thanks for everybody for sticking around. We're going to do something a little, I guess it's not super different, but we're going to talk a little bit about something that we are doing differently this year, or at least we had planned differently for this year. And I think we're definitely interested in trying to expand upon this effort in future years. So we want this to be a really collaborative conversation with you all. And feel free to ask questions, offer opinions, and jump in whenever something comes across your mind. So I'll just give a quick introduction, and then the other three folks up here will, I think, do the majority of the talking because they did the majority of the hard work to get this stuff prepared and make some decisions on the Jupyter Notebook proceeding submissions. So just to give a bit of context, you know, this is, I think, the second or the third, I think it's the second of these conferences that I've chaired. I can't remember. You know, Davide Del Vento, some of you probably remember, was the chair before me. And we've done sort of just written proceedings for each of these conferences. But we had noticed that over time, I think the submission rate was declining somewhat. And we thought that that would be, that would sort of be a good motivation to try something different. And we know that, you know, we've seen that other agencies and conferences are exploring the idea of doing interactive notebook submissions for proceedings, with the idea, you know, being that you can have something that's potentially reproducible, have something that has code directly embedded inside of your, you know, proceeding artifact. And it really is, I think, where a lot of science is going. And since we are producing software or supporting software that supports science, you know, it's sort of nice to, I think, use the same tools that our users are using. So last year, this was brought up as an idea by another person on the ISS committee, Wei Ming. Not sure if he's online right now, but he was a proponent of trying this last year. And quite frankly, we simply just didn't have enough time to put something together. And we did our old style of proceeding. But this year, I think we had more of a consensus that this would be an interesting thing to do. We still didn't have enough time, I would say. And that's why I think we got some of the details out to you all just a little later than we would have liked. And I've no doubt that that impacted people's ability to really digest it and say, oh, I'm going to give this a try. But we thought having this discussion, sort of presenting what was put together, some of the ideas we have, and then again, hearing your feedback would help prepare us to make this a success next year. So I think that's probably enough introduction, and I will hand off to Negin, who's, I think, going to overview some of what our sort of subcommittee worked on. So thanks.
Hello, everyone. My name is Negin Sobhani, and I work in the consulting services group in CISL, NCAR CISL. And I was part of the SEA ISS committee this year, and the idea of notebook submissions were brought up, and Katelyn, FitzGerald, Keith, Haing, and I decided to work on some sort of a workflow to accelerate that submission and make sure that it's a smooth and seamless process. So I'm going to go over some slides that will cover the infrastructure that we have. Let's see. Okay. Awesome. Okay. The essence of science communication, if we think about it, what has always been to transfer knowledge and to communicate knowledge to other people and foster collaborations. And when I was looking for figures to add to this slide on the history of science communication, I find this one that shows the timeline from 200,000 years ago. And you can see how science communication has changed over the years. You can see 1665, the first scientific journal was published, and we have 1869, first Nature journal was published, and until now. And then despite all the technological advancements we have over the past centuries, I would say, the way that papers are published hasn't changed much. So if Isaac Newton was around and I would have given him papers from today, he would have said, yeah, I understand the format and everything. We digitize it, but we still use the same formatting, the same way that we were doing it, yeah, centuries ago. Yeah, Isaac Newton might ask, what's MLAI? But yeah, he'll understand the rest of it. So Yeah, the screenshot shows how papers, the PDF looks like these days. And probably they'll look like, they look better in a monitor, but kind of it shows the problems with static publications. And that's the reader cannot interact with the data. The reader cannot explore the data. And of course, it looks ugly. You can see like the supplemental material, it's the other way. So yeah, so we need better way for science publication and science communication and making sure it's reproducible. Yeah, reproducibility and replicability are two major cornerstones of science. And I really like this image from a science article, which shows the spectrum of reproducibility, where we have a not reproducible publication on one side and a fully replicable publication on the other side. And you can see what are the challenges, what is needed to be added to the publication so that it will be fully replicable. And we all know why reproducibility is good. So I'm not going to go over why we want reproducibility, but it's very important. And I really like this image from the Turing Way project, which shows all the hassles, all the obstacles that one might face when they want to reproduce another study's results. So imagine that's me in grad school. I didn't have beard, but yeah, I looked like that. But yeah, so it was hard to find data that was used for different papers. It was hard to find the codes. I had to contact authors for the codes, the data. They'll often share it in a zip file. It wasn't clear what's the metadata of those files. There were a lot of problems. And this image kind of captures all the issues with traditional paradigms of science publications. One very powerful tool for science communication is computational notebooks. And computational notebooks, for example, Jupyter notebooks, give authors an interactive platform for integrating their data, visualization, code, and attach a narrative to that. So they can communicate the science, the scientific output very well. So, and it also, of course, help enhance collaboration, help with reproducibility. It doesn't 100% answer the reproducibility challenge, but it helps with the reproducibility. And also help with the storytelling. But the traditional publishing paradigm kind of lacks that transparency and that reproducibility aspect. And yeah, and then we decided to use Jupyter notebooks. So you might say, okay, Jupyter notebooks, Negin, you're saying it's great, but I know there are a lot of pitfalls. So first and foremost, Jupyter notebooks do not render very well and preview optimally, especially like if there are pull requests in a repository. And for answering that, we use Jupyter Book to automatically build the Jupyter notebooks and deploy them to GitHub pages. You might say, okay, Jupyter notebooks are not reproducible. And I wanted to add a figure that shows how not reproducible Jupyter notebooks are. Jupyter notebooks that are like just on GitHub. And one reason for that is that they do not have an environment attached to them. What are the packages that's used for creating that Jupyter notebook, the output on that Jupyter notebook? And is there a way to automatically build these notebooks into an HTML or not? And for that, we use GitHub Actions and we use Binder to create an environment. So each author needs to attach an environment file to their submission, but using Binder, it will create an environment for the reviewer or any reader so that they can interact with the elements of the notebook. And another big component, another big pitfall of Jupyter notebooks is that they do not have all the features that's needed for scientific publications. For example, they do not have cross-referencing, captioning. It doesn't work natively. So we use mist markdown to address that, but I'm going to cover that shortly. So this is something that I figured out actually just last night, but it seems like 3 weeks ago, the White House Office of Science and technology, they announced Project Jupyter as one of the winners of the Year of Open Science Recognition Award. And their category, which they were the winner, was technical advancements to enable open science. Yeah, Project Jupyter is an ecosystem. Jupyter Notebooks is one part of that. But this shows the potential that Jupyter Notebooks and Jupyter ecosystem has for enabling open science and reproducibility. So when we thought about the ISS publication process, we wanted to make sure it doesn't have that much overhead for the authors. It was the first year they are doing this, so we wanted to ensure that. We wanted to make sure that it works and renders nicely, and it produces an output that's very consistent between different submissions. And that we can create a proceeding at the end of the peer review process that would be very consistent. So the authors were to provide markdown files, and they can use markdown files if they wanted, if they want to use markdown, or they don't have interactive elements, or they can provide notebooks, or they can provide a combination of both, and then they can provide, and then they should add an environment file, either requirements.txt or a YAML file, and then the output will be a unified and a consistent format for the proceeding. Okay, so to address a lot of these issues, we started with the template repository. So the template repository, I added the GitHub link here. Yeah. So the template repository includes all the necessary styling file, all the GitHub workflows that's needed for building the Jupyter book, and all the files that the author needs for creating their submission. And it has two examples. One is, and I will show them later, but one is a more detailed example. The other one is a unified example. And then if the author needs to click on the, use this template to create their own template. And if they use this template for creating their submission, it will automatically build the rendered notebooks and the rendered markdown and displayed on GitHub pages using Jupyter Book. So the submission framework, if I want to summarize it, so each group of authors, they'll start their own repositories from the template repository. We have the UCAR SEA organizational GitHub. And under the UCAR SEA organization, there is this template paper repository, as I mentioned earlier. And then each author will start their own repositories. They add their markdown files, notebooks, they update the README to add their author information, abstract, the title of the paper. And then they commit the changes that they made, and they push it back to the repository, and it will automatically build it for them. So the review process internally for them would be very easy. And once they're ready for submitting the paper to the SEA, they have to create an issue on the template paper repository, and they'll create that issue, and we talk about that, the issue templates and everything later. And that signals us, that's kind of like signals the start of the peer review. That signals the submission, that the paper is submitted. Once the paper is submitted, the authors do not need to do much more. The peer review process will begin. The reviewer review the repositories. And once that step is done, we'll use a gallery generator to create a page that includes the links and the thumbnails for each one of these papers. And we publish a conference proceeding for this year. So it's kind of like a simplified process. And if I want to go over the details of like all the steps, and again, this is an overview of it. We have, first and foremost, we created a detailed submission guideline that's available online. I added the link here, and I'll show it later too. But the detailed submission guidelines should include all the steps that's necessary for the authors to create that. The estimated overhead from like starting to ending the submission should be around 30 minutes. So if you have already developed some markdown files for your submission, it shouldn't take you that long to create the submission. First, the authors create a new repository from the template. They add their notebooks markdown files. they update and the README, add the author names, the automatic deployment using Jupyter Book and GitHub Actions make it easy for them to modify it and review it. And once that's done, they create a new issue to transfer the ownership to SEA ISS to start the review process. And we have to mention that we borrowed that idea from the Pythia project. That's how they are handling the cookbook development also. So yeah. And then at the point that they are ready for the release and the submission of the project, you can create a DOI badge, and that's a requirement for all the submissions using Zenodo. Again, we have detailed explanation of what are the steps that's needed with screenshots and everything. And yeah. So for submitting the paper, okay. Okay. Yeah. So once your paper is ready for submission, the authors will start an issue. We created a template for the submissions. So they'll go to the SEA ISS template repository and click on issues, then click on get started, which should create an empty issue with them with all the fields that's needed to be filled. And you'll add all those fields in, and then it will give you also a checklist that the authors need to go through and make sure that they have addressed all the things in the checklist. And once that's filled, that's the repository or the paper is submitted technically. And Keith's going to talk about the gallery generator next.
This is the, I'm going to describe briefly the gallery generator component of this, which no one in this room will need to execute per se. This is more of the back end component. You know, as the submissions come in and you know, everything is accepted and we're complete with the process, this particular component of the system just generates the page that contains the summaries of all the submissions so that they can be directly integrated into the Jupyter book that would become the proceedings. And so this just shows a quick example. You know, we accept the submissions. There is a YAML file that that needs to be populated with the metadata for the submissions. That would be the title, abstracts, a few other things. And depending on how things are submitted, maybe we could automatically extract that. But you know, and then we run this utility that I built, ISGG or ISSGG, whichever one you want to use. And you can integrate that output directly into our proceedings page. It just emits a markdown file effectively. And then, you know, the ultimate goal is that, you know, I don't know for the people who have or have not used Jupyter Book here, in the end, the output of what we produce will be sort of more easily transformable, if you will, into things like PDF, HTML, et cetera. Okay, I don't think I'm doing the next slide. There we go.
So yeah, here are some screenshots showing some of the features that you can do with mist markdown. So so this is from a notebook cell from a Jupyter notebook, and it has mist markdown. And you can see you can integrate latex syntax for equations. You can use those, and it will automatically render that for you. And the screenshot should show that. So that kind of like address one of the weaknesses of Jupyter notebooks. I keep thinking that the laptop controls these slides. Another one is linking and cross-referencing. So you can see how here on the notebook cell with mist markdown, we are adding a figure. It doesn't have a caption and it's not referenced to like what number it is. But once this cell is rendered, it will automatically add a caption, and it will automatically reference that. And if I hovered over that link, it will even display the preview of that. And I can start sharing my screen to show some more of the features here. So seems like I don't have permissions to share my screen. Perfect, thank you. One. Okay. At first we were planning to do a live demo today, but I am smarter these days to do a live demo online when it's recorded. And yeah, last night when I tried it, it failed because of one of the dependencies. So yeah, I'm not doing a live demo. But you can see the template repository here. And there should be a link to the, yeah, here, this link, it has the GitHub pages and the rendered output. So yeah, so here you can see how the output looks like. And we have to say that we use the theme from Project Pythia. We modified it to use the SCA branding and adhere with UCAR branding. But yeah, again, shout out to Project Pythia. A lot of our workflows, not the GitHub workflows, but a lot of the thought behind this comes from Project Pythia and their experience. So you can see in here, which is the deployed page, and there is a how to use this template page. So this part has a detailed step-by-step guideline on how, like, you have to add your environment, you have to add your paper and the informations, update the README. And I'm planning to do a screen capture also of the process and put it on the page as well, in case that would be helpful for some of the authors. And then what the process is for submitting it and how to create a DOI for your paper and how you can configure binder for your paper. If you want to activate binder, you can do that. And then there are two examples I mentioned. One has like all the different sections of a paper in one notebook file. You can do that, or you can use a combination of Markdown and notebooks, or you can only use Markdown. It doesn't matter. So the example paper 2, it uses combination of Markdown files and notebooks. And you can see, for example, for the notebook pages, you have the binder capability. You can click on this, should start the binder for you. And then there should be a section on how you can reference other works and how you can create your bibliography for the submissions. See, here is the sample demo that we are technically doing. So an author that wants to start, they'll click on use this template, which should create a repository for them. They can choose the owner as themselves, or they can use the UCAR SCA. It doesn't matter. At some point, we're going to put everything under UCAR SCA. You can start with a private repository and then make it public later when you want to submit this. So yeah, the example submission is the page where I've already done that. Not sure why when I'm clicking on this, it doesn't work. But yeah, so you'll create your own repository, and then you have to clone that repository onto your local machine. Here are like it's what I've done just now, and like clone the repository, activate your environment that you have like everything in, and then open Jupyter Lab, or however, if you're using VS Code for modifying your notebooks, that should fine too. That should work fine too. And then let's see. And then, yeah, this is the opened Jupyter notebook. You can see, you can add like different contents here. Here it is. Okay. And let me go to the top level. Yeah, so when I open Jupyter Lab here, it will open up the top level repository. It shows all the files that are in a repository that's created from the template. If I am the author, I'll update the author names, author contact, abstract, everything. And then I'll add the information here. Here, for example, is the example of how the cross-referencing works and how it automatically creates the caption. You can see this is using mist markdown, and if I hover over this, it will show a preview of that image. Again, Jupyter Book automatically renders everything for you. If you want that, you can turn that off as well if you want to save your output and then submit it that way. So here is an example. It creates some data and then it plots it. You can use inline variable evaluation, which is a fantastic tool actually for scientific publication. So for example, imagine I have loaded a bunch of data and I want to get the maximum value of like monthly maximum temperature. I can write my sentence and then do an inline evaluation. So here I just did like inline and then this. So in case my data is updated next month, automatically the notebook that's rendered, it will show the updated values. I don't have to reference the values and type in the values in contrast to the old way of like publishing everything. You can add acronyms to your submissions. That's very powerful too. It automatically gives you the capability to add previews on GitHub issues or GitHub PR. So here, if I hover over this, it will show the issue or, yeah, and I can click on it so you can see how it looks like. It's very, very simple markdown syntax. And you can also use add footnotes, just an example of a footnote. You just have to add this with what your footnote is, and you can reference it then later. So here, when I do that, it will, when I hover over it, it will show what my footnote is. So yeah, there are a bunch of different cool things that one can do with notebooks. And you can use simple markdown files as well. Or if you prefer, for example, LaTeX file, you can also convert LaTeX file to markdown easily using Pandoc. But yeah, we can start the discussion and panel discussion. And for us, it was very interesting to also hear from you all to know what you think are their pain points and you think that are preventing everyone from doing this in different conferences and for different scientific publications. Stop sharing. So, Katelyn, do you want to start the questions?
Yeah, sure. So I think hopefully you should all be able to hear me. But I think for this part, we kind of envisioned hopefully something a little bit more of a two-way discussion. So we do have Slido open at this time, I believe. So go ahead and drop questions in there for the panel or comments and feedback. And I think people can upvote those. We pre-populated a few. But while folks are kind of thinking on that and working on some questions for the panel, I think more broadly, we'd be interested in hearing kind of general feedback on the Jupyter Notebook submissions from you all. And then also more broadly, and this is maybe a provocative question, but kind of getting back to Brian's commentary on kind of participation in conference proceedings, I think, you know, we're also interested in what, and again, more broadly, would make people more interested in and excited about participating in conference proceedings in general, or if there are specific barriers. So I'll leave you with those kind of broad questions, and then I think we'll start off with some questions if there are any on there. Okay, well, maybe we don't actually have any questions in Slido to be upvoted, but we do have a list up here, so we'll cheat. But it looks like someone's at the mic, so go for it.
So I've been using notebooks a lot. So one of the things that I noticed for this kind of thing is that if you want to, for example, you have a large data set and you want to do it in the notebook and show it on Binder or anything, then you have to find a place to store your data and then have public access to it. So is there anything that you can do for this kind of things?
This is a fantastic question, and this is something that I've seen other conferences also struggling with when they are advocating open sciences. Who's going to pay for that storage online? We don't have an answer to that ourselves because at some point, someone needs to be responsible for paying for that storage, especially for large storages. If they have like a large data set. There are some resources that you can use for a smaller data set to host it. But for larger data sets, if there are climate data sets, some of them are hosted on public. For example, Amazon S3 has CMIP data set available in a bucket, but and that those can be used. But mostly, it's an issue that needs to be addressed. I don't have anything else to add, but if
Yeah, I was gonna say, yeah, that's definitely an issue that is not solved. You know, Zenodo allows uploads of pretty large. If you want to try, and you get a DOI, which is great, so you can actually cite appropriately. Yeah, but yeah, this is kind of the problem that needs to get solved. That and the execution environment, which is much more challenging problem solve. Yeah.
I just want to add to, and I mean, this was something that actually Keith talked about a lot too when we were kind of having some initial discussions about this, but there are also some, certainly some questions with data in regards to kind of like reproducibility and replicability too. And ideally you would want like some sort of a DOI associated with that data, right? And some other things. And so there's just some additional infrastructure to kind of get worked out. I think it's still very much an active and open question that a lot of these types of groups are grappling with. I see Julia nodding.
I think the thing that probably stopped me from, submitting a notebook is that I don't really work in Python, and a lot of the stuff I do is just shell scripts, that sort of thing. And I know there's some of that kind of functionality in the notebooks, but at that point, then it's like I don't quite have enough time or bandwidth to think about, okay, how can I take what I'm doing and translate it into that? So maybe one thing to consider would be like, even if you can't necessarily do much in terms of like the infrastructure. I mean, the notebooks kind of are what they are, but even just having examples of like, oh, here's how, whatever, here's how somebody came up with an interesting way of presenting what they're doing either on the command line or like, I don't know if Jupyter notebooks have like nice rendering for other kinds of code, like, compiled, like pretty ways to present C or Fortran code. But if I knew about those things and if I could see examples of those things, then I think it would make it more easy and more motivating to submit that sort of thing.
Thanks. Thanks so much. That's a great point that you brought up. And there are some kernels available for different languages, and there are ways to kind of like reference a Fortran file, for example, a snippet of a Fortran file or a snippet of another file that's in that repository. But I agree, more examples of usage on how to use that would make it a lot easier for others to use that. There is you can easily add a shell kernel that runs your technically shell commands for you in a notebook environment. But again, I agree, we should add an example on that, how to use that. So yeah.
Can I add one more thing? There's a tool, ASCII Enema, or I'm not exactly sure how to pronounce it, but it's a tool that you can record your terminal sessions, and it will give you a animated GIF or SVG or something like this that you can drop directly into your Markdown if you wanted to. You may have seen GitHub pages where there is a playback of the actual script. They're using this tool. So you might want to check that out. And for other people who may have similar, requirements, you can just basically do a screen record of your terminal, and then it'll output into a form. You can drop it directly to HTML or Markdown. Yeah.
But I guess it sounds like the takeaway, Alex, from that comment is that it's just a matter of seeing capabilities for this, for this community and the types of things that we're presenting here, where it's like, oh, I couldn't have done that in a nice way with a traditional publication. And that would be motivating.
Yeah, next question.
Okay. So in general, my team uses Jupyter notebooks a lot, in particular for education and for training purposes, which we do a lot of. And in principle, I really like the idea of being able to submit notebooks to conferences. What gives me pause, though, is that a lot of the things that we do in Jupyter notebooks involve calling APIs, external APIs, that change over time. And so if we were to publish a notebook today, that API could change tomorrow. And maybe it would, maybe with versioning and things like that, it would probably continue to work for a little while. If we, told it that we wanted the old version, but in a year or so, they'll probably stop supporting that version of the endpoint, and it would no longer work. And it's kind of been baked in now. And so, that's one of the things that concerns me about the idea of kind of putting a notebook in amber and preserving it for the for the ages.
Yeah, I was going to respond to that real fast. So this is a problem that I'm intimately familiar with because I teach a class where I have submissions where APIs are being used, and this recently happened where the API completely changed. And in fact, the data was reduced by a factor of 10. Okay, so all of a sudden, what should have been something like maybe 7,000 or 8,000 data points dropped down to 70, something like nothing. And as I was preparing the notebook and rerunning it to give it to a grader to grade the other submissions, I realized that all of a sudden this data is gone. And luckily, I had a copy of the file. So what I was going to say to this was one of the things that I try to encourage and try to do myself is when you just sort of separate these notebooks out into sort of your API to output, and then your processing notebooks use that original output just in case that API goes away. Because in my case, the arrangement with the API provider, they were aggregating data from other sources, and legal guidance, something happened and they could no longer provide the data that they were providing just a week prior. So, maybe if at all possible, and the other interesting thing about if you have this API output and you store it, then if it's legal to do so, you could then put it somewhere where it becomes a permanent and referenceable data set that also represents the slice of that data because now we're getting into, okay, I have this huge set of data that I need to work with, but I'm only working with a subset of it. I'm working with a slice of it. So which slice is the slice that I need to use and if that slice changed, now I can't actually get the exact same results that you did, et cetera, et cetera. You see how that just kind of collapses pretty fast. So yeah, the recommendation that I'm always suggesting is to, especially with API stuff, if possible, just stored in a separate notebook that does that API stuff, and then your output, corresponding output files can be consumed by the processing notebooks. Yeah. And it's, with many of these APIs, you just can't go back in time once they make the changes, so.
Yeah, I think to kind of add to that, I think that's a really interesting question, and I think it also really depends on kind of what the objective is with the conference proceedings and what we want, I guess, what you as an author want, and then what also kind of we're interested in, providing to the consumers, I guess, for lack of a better word. I think there's some interesting, so for example, with like Project Pythia, and again, Julia's in the audience, and I believe some other contributors to the Project Pythia cookbooks are probably around as well. They have some infrastructure that kind of does regular testing to make sure that kind of things are actively working, and then there's badges that indicate whether they are or not. But if you have something that is broken, even if it tells you it's broken, if no one is looking or fixing it, then there's some additional, I guess there's some additional kind of like monitoring and maintenance burden. And I think maybe the bigger and first questions are kind of what are we actually looking to get out of these conference proceedings? And if it does work even for a short period of time and demonstrates some interesting features, is that enough for us, right? So I think, anyway, feedback on those types of questions would be very welcome.
Yeah, I'd like to share a little bit more about Pythia's experience with this sort of thing. So, I mean, data buckets for storing data is always a challenge, and we're working with 2I2C to kind of try and find solutions for larger data. Again, most of the time, downloading the data, seeing if you can store if it's small enough in the repository, using data sets that are small enough to be in a tutorial module of a function. But when we're trying to teach people how to use Dask and parallel processing, you kind of defeat the purpose a little bit. And so that's, it's a big challenge that no one has the answer to. And then this piece about the API changing and the fear of Jupyter notebooks not working it's a smaller piece of kind of a larger question we have with Jupyter notebooks, is that while there's an environment file, we don't have the exact packages that were used. Like not every single package is pinned. They're all set to like the latest, and ones that are pinned that need to be. And so you can maybe save this file somewhere. But in the end of the day, we decided that we do not want to pin things. The Jupyter notebooks are not static, and we're not going back in time. Like, we just live in a world that the science is moving forward, and we want our learning resources to show what the tools are currently. And so with that, the DOI kind of addresses that problem by creating this static resource that you're looking for. It creates a version of the HTML with the code that works, with the HTML that works. Yay, and you can always go to that and people can tell you exactly which one they're referencing. But yeah, ultimately the Jupyter notebook, what's good about it is that it is evolving. And then another challenge we have with DOIs is that they're citable, but they're not exactly findable the way something published in Nature is. So we're considering doing something that maybe sounds slightly backwards. Like we're moving from this place where you can interact with the data and maybe use like hvplot or something on the website to then talking about creating a special publication with a traditional journal that happens like once every year or something with all of the new or updates to old cookbooks, which is what we call our Jupyter books. And so that would create a very static traditional publication, but then that could direct people to the more living. So yeah, these are big questions, and it's really hard.
Thanks so much, Julia. Yeah, we struggled with these questions a lot when we were trying to think about how we want to do that. For the SEA, and I think for maybe like scientific publications, we really maybe, I don't know, like I think For SEA, we deactivated the nightly builds or weekly builds because that's something that Project Pythia does, which is very, very good. It nightly or weekly, nightly Project Pythia, it will build the notebooks to make sure it still works. That's fantastic, but for a scientific publication, with the packages being updated, the result might be even different. So like in 10 years from now, I don't want the result of my publications to be different. So we decided to turn off that so we'll render it once, and once it's published in the proceeding, it's not gonna redo that. So at least for SEA, we made sure that that part is in place, but it reduced the reproducibility. And so if someone wants to create the environment again or use Binder, it will not. They should maybe add like maybe we should add something on like just freezing that environment. So the specific package versions will be specified. Maybe that's something to do with some of these scientific publications.
I was just going to say, I think our top rated online question really kind of dovetails nicely into what you're saying, Negin. So I'll just read this and then we can jump into this. Do you require any kind of dependency management for Python, for example, Conda, on your submissions to ensure that the notebooks are actually reproducible? Without using those tools, it's very difficult to reproduce the required environment to run the notebooks. So thanks, Maxine. And yeah, what sort of environment.yaml/other requirements were discussed?
Thanks so much, Maxine, for the question. I want to shout out to Haing Zhu, who is not here. She is one of the people on the committee, but she was out of country. So the way that we decided to go about it, at first we were just using pip, but thanks to Haing, we implemented both pip and Conda, so the user can do either or. Hopefully that will be helpful. I don't know. Because I know some users like pip better and some users like Conda better. I myself prefer Conda every day. But.
I think this is I mean, I guess going back to the thought about compiled code, though, this is maybe an area where we could put some additional thought into kind of how we might maybe have an example or template for how one would approach that as well. And now thinking about it too, we certainly, even back a few years ago, we put together a whole bunch of notebooks for like Hydro model training. And that was all in a containerized environment. And we were running kind of, Fortran model code through those notebooks. So certainly an option.
Okay, so I work at Cosmic. This is a GNSS lab, and last year we had a workshop, and the first time we used Jupyter Notebook as tutorials and everything, and it was very interesting because we had all different types of levels of people experience with Jupyter Notebook. Some of them very, very experienced, and some of them was the first time that they saw that. Also, some people had administrative rights on their computer, so they could play with Conda, they could download anything they wanted, and some did not. We had as well a server where users that could not do the Conda on their computers, they could use the servers for data manipulation. What I'm trying to say, I think this is a brilliant idea personally. And I think this is something that it's gonna happen in the future. 10, 20, 30 years, this is gonna be it's gonna happen. Maybe it's not gonna be called Jupyter, but for sure it's gonna happen. But I think like the use of templates, or they used to do like, what do I do if I've never seen Jupyter before? How do I learn this? What do I do if I don't have rights to my computer? Those questions are very important for users. So I just think it's important to address them.
Thanks. That's a great point that you brought up, and I agree. These are great questions that needs to be addressed. I myself thought about people who are not familiar with like Markdown or notebooks, and like we need to add a procedure how to create a Markdown from a Word document. But something like that would also be very, very helpful for users. I agree.
Yeah, no, thanks for that input. I mean, I think that there's some additional kind of maybe like walkthrough or tutorial information that could be added. And then I guess I also just wanted to add too, I don't know that we demoed this, but we at least tried to set up some of the template submissions so that they could run on like Binder Hub, so that for folks who wanted to check out the submissions more interactively, they had an option to do that. That was not necessarily on their own machine. There's some challenges there too, but it's at least an option for some things. I think I've also noticed a trend towards kind of more like in-browser stuff and interactive examples, and that's a pretty cool space as well.
I'll add one more thing. One thing I've noticed as well is that different disciplines have different patterns, workflow patterns, data patterns, computational patterns. And so this is one of those areas that has to also get addressed because, you know, I've worked with groups in you know, sort of the biomedical, and they do things they think about data. The idea of what data is may vary quite greatly, just at that level. You know, data is not what you think it is, or it's this thing only, or whatever. So that's also an area that I think we're lacking some maturity, perhaps, because, you know, one workflow doesn't fit all, one conception of data doesn't fit all, et cetera, et cetera. So yeah.
Okay, I'm just going to ask some pulse questions of the room that we had talked about before. You know, since this is an audience that, and I know we probably have a few scientists here, but it's a lot of software engineers and technical folks. Just raise your hand if you've used a notebook. Okay, raise your hand if you've written a notebook. And then raise your hand if you've submitted a notebook for any purpose. Yeah, I think we're sort of in the early stages of that last one. So, you know, Negin and I went to the US RSE conference last year, the first one, and they did notebook submissions there. And I think that was part of our inspiration. And obviously AGU, you know, the American Geophysical Union has an effort to adopt notebook proceedings and notebook submissions. So, you know, I think this is something that's going to grow, but a lot of these questions are tough. Thanks. And I guess I'll read, I think we have another online question. So one of the themes for this year's conference was modernizing software development practices, and we've had several good talks focused on using various different tools. How do you envision these more technical show and tell type talks working with Jupyter Notebook proceedings? I think it's a great question, and I'm curious to hear what our panel says.
I'll start. Yeah, but I'm definitely not going to fully answer this question, so hopefully other people can chime in. I think so. This is a great question, and it's one. I think a broader question I've also wondered about is kind of what the relationship between kind of presentations and different types of presentations and notebook proceedings should be. You know, if that should necessarily be, you know, one-to-one, or if people should be able to, you know, like if notebooks might be another way to kind of present your work or something like that. But back to the question. Yeah, so I mean, I think you could, I mean, conceivably you could link to other more interactive components. I mean, that doesn't get you much beyond kind of like what a PDF with links would necessarily. But you could certainly incorporate additional like interactive visualizations, or some of the kind of like screenshot tools, you know, beyond what Keith was talking about, but in addition to, I guess. So those are conceivably options. I think you could probably get more creative and include potentially other types of content, but this could also, I think there's nothing to say that this needs to be more than just kind of a text summary or kind of the content of a traditional conference proceedings either. So, you know, if that's what you wanted, you could have it be that as well. There's just the ability to incorporate additional kind of interactive content and code.
Yeah, I think that's part of the reason that Negin showed, the two examples at the beginning. So the one was really just a pure markdown example. And I think it's an open question for all of us, is that something that adds enough value to be worth the upfront cost of sort of understanding the infrastructure and using a technology that maybe you don't use in your day-to-day life? I mean, if you are notebook native, then great. But if you're not, then obviously we understand that that adds a little bit of burden. But there are some things I think that are gained there as well. Like if you have a block of code, with some of the tools that are integrated into that ecosystem, you can get some very nice code formatting and colorization and things like that. So even if you're not doing it in an interactive context, there are some nice quality of life features that once you learn how to use them and use them in a powerful way, I think they can be time savers, but it's just a matter of getting people comfortable with it. It's sort of like if you like using, LaTeX, it's probably like, it's super great and easy. And I know some people who do. I don't. So when I look at, that code, I'm like, oh man, I'm going to go back to Google Drive or Google Docs. But, it's all a matter of being comfortable with the tool, I think. And, that's, I think, partly on us is helping people be comfortable with the tools for submitting these notebooks. So. So I do notice that we are at 3 minutes. So if anybody has any sort of final question or comment on the panel that they want to bring up.
There was one.
So top rated? Yeah, so is there going to be documentation how to set up the environment for the Jupyter Notebook or to link to existing document or content, I assume?
Sure. Yeah, the how to use this template that should have that guideline. But another thing that I thought would be useful would be just a screen recording of me going through all those steps, trying to do them, and then add it on that guide as well. So I'll do that too and make sure that's posted. But yeah, the how to use this template guidelines that was on that repository and that I shared should have that as well.
Yeah, and then maybe we can address Anthony's question as well. So do you foresee any issues with a push of Jupyter Notebooks being a presentation documentation method shredding into becoming the software solution? For example, use this notebook as a script in lieu of any other tool.
That's a great question. Everyone else answer, because I hate to see that myself too.
I guess personally, I think that there's still space. I mean, the notebooks and the tooling around notebooks, particularly in kind of context where you're presenting material, provide some niceties and some consistency that maybe you wouldn't have otherwise. But certainly there's still a space for scripts and other mechanisms to run code.
Let's see. Yeah, there we go. Yeah, I think that you can't replace. There are so many things in an individual ecosystem and workflow that I don't think Jupyter could fully replace everything. People are going to try though.
I guess I'll also add that I don't know, I mean,
it's a tool, right? So yeah, you can do all sorts of fun things with it, but is it the right tool for every job? No. And can you use it poorly to give a presentation or a training? Sure. So I think, you know, yeah, I mean, there are a lot of great things you can do and there are a lot of terrible things you can do, like any tool.
I was just gonna wrap things up, Negin, so if you wanted to add one more thing, go ahead.
One last thing I wanted to add, one last point is that I've already seen that trend happening of at least like the users that I talk with, a lot of them are moving to just purely use notebooks for doing everything. So if that is already happening, then the scientific publication, the method that we are doing it can use that and leverage that. I think that's also already happening outside of like enabling scientific publications using Jupyter notebooks. But yeah, I myself do not like to see that trend as well. So yeah.
Right, thanks. And I did want to, I guess, maybe to echo what Katelyn said in her last comment, you know, it is just one tool of many. And this year, you know, we really sort of familiarized ourselves as a committee on what the challenges and opportunities would be. I think we're certainly interested in trying this again next year for this conference and maybe seeing then what the, you know, our community's experience is like. But I don't think it's our intention to force anything on anyone. Just, you know, like notebooks are the future, so we will all assimilate. So we're gonna send a survey out to everybody who attended, just generally about the conference. We do this every year. But one of the questions certainly will pertain to using Jupyter notebooks as a publication artifact in the future. We'd appreciate any thoughts you have on that. And if the thought is like, I would be more inclined to submit something that's a traditional format, I think that's useful feedback for us. So don't worry about, you know, give us the unvarnished truth. But also if you are excited about it or potentially excited about it, and there are things that would make it easier or make you more interested, that's definitely something we'd like to hear about as well. I also just wanted to thank, you know, everybody who worked on this effort. So, you know, Negin, Katelyn, Keith, and Haiying, who couldn't be here. You know, we decided as a committee that we were interested in this, and then I personally was like, I don't have time. So they all graciously volunteered and really pulled a lot together in a short period of time. So let's just give them a round of applause. All right. So that wraps us up for today. I appreciate you sticking around and participating in the conversation. Obviously, we have one more day in the conference, so we have a bunch of good talks scheduled for tomorrow, and we'll hope to see you at 9 a.m. And I guess I'll give the daily reminder. Tasia, do we have any leftover food out there is the question. Okay, there's still some fruit out there, so nice and healthy parting gift. So we'll see you tomorrow, everybody.